Bởi vì nó chi thì mình đã cung cấp đủ thông tin để vào việc mà được thì nó chỉ có phần API là mình tự cung cấp thôi, còn nào cái còn như luồng luồng đẩy CPI ra rồi cái phần mô tả luồng vào thông tin thì mình có cái thông tin đó được. Tức là mình hỏi hỏi vẫn đã thực hiện đây thì còn cái chỗ mà đối chữa thì nếu mà bây giờ mình tìm một cái giải pháp để mình chuyển hoặc là thì mình có thể một cái mình từ đang đi cái lên thì nó tập nó chảy được cái sau thì bây giờ mình phải đi chỉnh từ cái có chân lên đấy thì vẫn là đang làm bên trong đấy cái chỗ mà làm bên trong là mình chỉ từ cái tất cả chỉ trên bây giờ đến hết thì là bây giờ đứng ngân cái thử là cái tà từ rớt lên một vườn nếu không cần mới bao giờ cái cái đảm bảo chất lượng cái tiến độ nói chung là việc là ta đảm bảo được cái chất lượng với cái tiến độ rất rất thời gian bốc lên những cái khác nó tối thì nào những người kia thì mình được Sang sang sáng nay tao đuổi đi tháng thôi rồi còn mình thì cái đưa các chế thì mất là để thôi để cái tết mấy cái mình thiết kế ở VTC cần tốt thì trong thị trường mình sẽ để tốt lên 25 ngày 23 45 là nó kích hoạt. Không biết dự kiến là một không dự kiến là một cái mảng cái tin đang xin thì nó tạo nó đã đang bảo này không cần người ta sẽ biết. đâu đã đi là gặp lại các cái vô vòng đâu có bắt đầu qua cái ra đổi mình mà cái nhận start ở đầu đấy và em có là rất rất anh anh xích cái đấy cái lồng slide mình và em đọc bình thường là chứ rằng cứ Chắc tôi có thể là cái tài liệu đấy nó tôi mới dịch xuống được suốt cho thôi. Thì cái này là bây giờ anh biết cái tài liệu người Việt này có bao gồm chỉ có 5,4 tỷ chứ không mà tỷ Việt thì qua đâu cái chắc là cái trình bói phép người dân mang cần được những cái bản trên cái sự thật có trên tôi được cái ghế có thì mình tiếp tục mình sẽ chuỗi để người chắc là được chuẩn kho voi thì mình làm đầu tư thì nó đã có bước làm chơi phần cho đến một túi đèn mà biết anh được sức nhớ rất như đi này lên một nhân sự mới vào của chính này thì các cháu sử dụng đi ở trên digital không cũng cái tự điều có người đại biểu dân mai được người thì cao cái vừa chúng cao cho cái bằng nó theo từng ngon bây giờ mà có họ về cái điều rồi với đây chúng ta đã quá nhiều có điều đa bằng mà nó thành kinh người được nếu mà biết về nếu mà nó chỉ đại vào cái mốt trong vật phẩm là hoặc là cái trước kia phải sau khi ta nguồn cả là robot thì cái lần đầu đặt mà nó tôi nắm rõ về nó phải chỉ mình sẽ có hoạt động là mình chỉ biết từ đầu trên cao viết thì bây giờ vận hành mình trên cao viết học làm sao mình nghe là trong đó chỉ nghĩa là nó cũng được phải có như suy nghĩ cùng cái giải thích là hoàn hảo để lâu hơn thì là còn nếu mà thì đừng bị hơi về văn học hay như là nếu mà quan trí thì mà quan văn học thì như là cái mà nó còn mình sáng nó hoàn lại nó ngoài chính của thì là mặt thì tất cả như những người là môn luôn việc nào rồi đã để tổ trang một thiếu rồi thì cái đời đi tiếp theo mình ăn thì mình sẽ để đi để kiếm trên tôi cho ở ra đi đấy thì về con là từ đó anh để tìm biết được con được phải có phải đi thiết kế cho nên là bạn đặt mình anh này có và cái bạn nói chia thì theo là hết cái đạo của đã đi là hiện tại bạn đã làm cái này nên sang phương án có thể là cái chính phải luôn thì muốn tin thì stop xem là thì đưa lại sang cái trang tin nhiều yang di akhirnya tentang làm thì cái sự phê bình là cái tiền
Sao mình kể gọi tiến sĩ đấy là chuyện không phải
chỉ trong những cái mình hay làm nội thất liên tục thế thì kiểm toán như thế mình làm khi làm xong cái đấy thì nó đã biểu có chung đi nữa thì bây giờ chỉ là thành một lý ngay công việc như thế mình làm cái đúng cái có biểu ra như thế chân nào rồi là cái việc tôi đặt cái rồi lý là có đối với người đến trường lớp này các điều này thì là cái điểm ngon đối với cái đường chỉ yêu là con là tìm kiếm cái điểm để cho mình làm thì cũng để làm đây nhưng bây giờ là đi anh làm tốt cái điều và nghĩ là ở trong đầu cũng có cái như là nó là ta bây giờ trên kinh tế đủ lên thì mình vào cần những chuyện thì là mình chỉ nói những cái bao bì hắn như là ví dụ như là đầu làm gia đình mình thôi là mình đang chỉ bản thân hay có những bằng những người em trẻ con ngoài là khi con chưa có nhiều mang suy nghĩ không nghĩ đến đó anh mình suy nghĩ là anh có phải gì đó thì mình có nhưng mình là không phải cái gì còn có biết có nghĩ ra thì mấy thì mình thấy tiền thật thì ta cho là tiền cái phần thì ở cách làm việc biệt cái tập thì con phải là cách lên lên
Recurrent neural networks, you just unroll them. Bam. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about recurrent neural networks and they're going to be clearly explained. Lightning and grid.
Mente geniales.
check them out when you've got some time. Note, this StatQuest assumes that you are already familiar with the main ideas behind neural networks, backpropagation, and the RailU activation function. If not, check out the quests. Also note, although basic or vanilla recurrent neural networks are awesome, they are usually thought of as a stepping stone to understanding fancier things, like long short-term memory networks and transformers, which we will talk about in future StatQuests. In other words, every quest worth taking takes steps, and this is the first step. So, with that said, let's say hi to StatSquatch. Hi. And StatSquatch says, "Hello. The other day I bought stock in a company called Get Rich Quick. But the next day, their stock price went down and I lost money. Wah wah. So, I was thinking, maybe we could create a neural network to predict stock prices. Wouldn't that be cool?" That sure would be cool, Squatch. Unfortunately, the actual stock market is crazy complicated, and we'd probably both get in a lot of trouble if we offered advice on how to make money with it. But if we go to that mystical place called Statland, things are much simpler and there are far fewer lawyers. So let's build a neural network that predicts stock prices in Statland. However, first let's just talk about stock market data in general. When we look at stock prices, they tend to change over time. For example, the price of this stock went up for 4 days. Hooray! Before going down. Wah wah. Also, the longer a company has been traded on the stock market, the more data we'll have for it. For example, we have more time points for the company represented by the blue line than we have for the company represented by the red line. What that means is, if we want to use a neural network to predict stock prices, then we need a neural network that works with different amounts of sequential data. In other words, if we want to predict the stock price for the blue line company on day 10, then we might want to use the data from all 9 of the preceding days. In contrast, if we wanted to predict the stock price for the red line company on day 10, then we would only have data for the preceding 5 days. So we need the neural network to be flexible in terms of how much sequential data we use to make a prediction. This is a big difference compared to the other neural networks we've looked at in this series. For example, in Neural Networks Clearly Explained, we examined a neural network that made predictions using one input value, no more and no less. And if you saw the StatQuest on neural networks with multiple inputs and outputs, you saw this neural network that made predictions using 2 input values, no more and no less. And in the StatQuest on deep learning image classification, you saw a neural network that made a prediction using an image that was 6 pixels by 6 pixels, no bigger and no smaller. However, now we need a neural network that can make a prediction using the 9 values we have for the blue company, and make a prediction using the 5 values we have for the red company. The good news is that one way to deal with the problem of having different amounts of input values is to use a recurrent neural network. Just like the other neural networks that we've seen before, recurrent neural networks have weights, biases, layers, and activation functions. The big difference is that recurrent neural networks also have feedback loops. And, although this neural network may look like it only takes a single input value, the feedback loop makes it possible to use sequential input values, like stock market prices collected over time, to make predictions. To understand how, exactly, this recurrent neural network can make predictions with sequential input values, let's run some of Statland's stock market data through it. In Statland, if the price of a stock is low for 2 days in a row, then, more often than not, the price remains low on the next day. In other words, if yesterday and today's stock price is low, then tomorrow's price should also be low. In contrast, if yesterday's price was low and today's price is medium, then tomorrow's price should be even higher. And when the price decreases from high to medium, then tomorrow's price will be even lower. Lastly, if the price stays high for 2 days in a row, then the price will be high tomorrow. Now that we see the general trends in stock prices in Statland, we can talk about how to run yesterday and today's data through a recurrent neural network to predict tomorrow's price. The first thing we'll do is scale the prices so that low equals 0, medium equals 0.5, and high equals 1. Now let's run the values for yesterday and today through this recurrent neural network and see if it can correctly predict tomorrow's value. Now, because the recurrent neural network has a feedback loop, we can enter yesterday and today's values into the input sequentially. We'll start by plugging yesterday's value into the input. Now we can do the math just like we would for any other neural network. Beep, boop, boop, beep, beep, boop, boop. At this point, the output from the activation function, the y-axis coordinate that we'll call y sub 1, can go 2 places. First, y sub 1 can go towards the output. And if we go that way and do the math, beep boop boop, then the output is the predicted value for today. However, we're not interested in the predicted value for today because we already have the actual value for today. Instead, we want to use both yesterday and today's value to predict tomorrow's value. So, for now, we'll ignore this output, and instead, focus on what happens with this feedback loop. The key to understanding how the feedback loop works is this summation. The summation allows us to add y sub 1 times w sub 2, which is based on yesterday's value, to the value from today times w sub 1. In other words, the feedback loop allows both yesterday and today's values to influence the prediction. Hey, this feedback loop has got me all turned around. Is there an easier way to see how this works? Yes, there's an easier way to see what's going on. Instead of having to remember which value is in the loop and which value is in the input, we can unroll the feedback loop by making a copy of the neural network for each input value. Now, instead of pointing the feedback loop to the sum in the first copy, we can point it to the sum in the second copy. By unrolling the recurrent neural network, we end up with a new network that has 2 inputs and 2 outputs. The first input is for yesterday's value, and if we do the math straight through to the first output like we did earlier, we get the predicted value for today. However, as we saw earlier, we can ignore this output. The second input is for today's value, and the connection between the first activation function and the second summation allows both yesterday and today's values to influence the final output, which gives us the predicted value for tomorrow. Now, when we put yesterday's value into the first input, and we do the math just like before, then we follow the connection from the first activation function to the summation in the second copy of the neural network. Now we put today's value into the second input, and keep doing the math. And that gives us the predicted value for tomorrow, 0, which is consistent with the original observation. In other words, the recurrent neural network correctly predicted tomorrow's value. Bam! Likewise, when we run yesterday and today's values for the other scenarios through the recurrent neural network, we predict the correct values for tomorrow. Double bam! This recurrent neural network performs great with 2 days worth of data. But what if we have 3 days of data? When we want to use 3 days of data to make a prediction about tomorrow's price, like this, then we just keep unrolling the recurrent neural network until we have an input for each day of data. Then we plug the values into the inputs, always from the oldest to the newest. In this case, that means we start by plugging in the value for the day before yesterday. Then we plug in yesterday's value, and then we plug in today's value. And when we do the math, the last output gives us the prediction for tomorrow. Bam. Note, regardless of how many times we unroll a recurrent neural network, the weights and biases are shared across every input. In other words, even though this unrolled network has 3 inputs, the weight, w sub 1, is the same for all 3 inputs. And the bias, b sub 1, is also the same for all 3 inputs. Likewise, all of the other weights and biases are shared. So, no matter how many times we unroll a recurrent neural network, we never increase the number of weights and biases that we have to train. Triple bam! Okay, now that we've talked about what makes basic recurrent networks so cool, let's briefly talk about why they are not used very often. One big problem is that the more we unroll a recurrent neural network, the harder it is to train. This problem is called the vanishing/exploding gradient problem, which is also known as the "hey wait, where'd the gradient go? Kaboom!" problem. In our example, the vanishing/exploding gradient problem has to do with the weight along the squiggle that we copy each time we unroll the network. Note, to make it easier to understand the vanishing/exploding gradient problem, we're going to ignore the other weights and biases in this network and just focus on w sub 2. Also, just to remind you, when we optimize neural networks with backpropagation, we first find the derivatives, or gradients, for each parameter. We then plug those gradients into the gradient descent algorithm to find the parameter values that minimize a loss function, like the sum of the squared residuals. Bam! Now, even though the vanishing/exploding gradient problem starts with vanishing, we're going to start by showing how a gradient can explode. Kaboom! In our example, the gradient will explode when we set w sub 2 to any value larger than 1. So let's set w sub 2 equal to 2. Now, the first input value, input sub 1, will be multiplied by 2 on the first squiggle, and then multiplied by 2 on the next squiggle, and again on the next squiggle, and again on the last squiggle. In other words, since we unrolled the recurrent neural network 4 times, we multiply the input value by w sub 2, which is 2 raised to the number of times we unrolled, which is 4. And that means the first input value is amplified 16 times before it gets to the final copy of the network. Now, if we had 50 sequential days of stock market data, which, to be honest, really isn't that much data, then we would unroll the network 50 times. And 2 raised to the 50 power is a huge number. And this huge number is why they call this an exploding gradient problem. Kaboom! If we tried to train this recurrent neural network with backpropagation, this huge number would find its way into some of the gradients. And that would make it hard to take small steps to find the optimal weights and biases. In other words, in order to find the parameter values that give us the lowest value for the loss function, we usually want to take relatively small steps. Bam. However, when the gradient contains a huge number, then we'll end up taking relatively large steps, and instead of finding the optimal parameter, we'll just bounce around a lot. Wah wah. One way to prevent the exploding gradient problem would be to limit w sub 2 to values less than 1. However, this results in the vanishing gradient problem. Hey wait, where'd the gradient go? To illustrate the vanishing gradient problem, let's set w sub 2 to 0.5. Now, just like before, we multiply the first input by w sub 2 raised to the number of times we unroll the network. So if we have 50 sequential input values, that means multiplying input sub 1 by 0.5 raised to the 50th power. And 0.5 raised to the 50th power is a number super close to 0. Because this number is super close to 0, this is called the vanishing gradient problem. Now, when optimizing a parameter, instead of taking steps that are too large, we end up taking steps that are too small. And as a result, we end up hitting the maximum number of steps we're allowed to take before we find the optimal value. Wah wah. Hey Josh, these vanishing/exploding gradients are a total bummer. Is there anything we can do about them? Yes, and we'll talk about a popular solution called long short-term memory networks in the next Stat Quest. Kabam! Now it's time for some shameless self-promotion. If you want to review statistics and machine learning offline, check out my book, The StatQuest Illustrated Guide to Machine Learning, at statquest.org. It's over 300 pages of total awesomeness. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you want to support StatQuest, consider contributing to my Patreon campaign, becoming a channel member, buying 1 or 2 of my original songs or a t-shirt or a hoodie, or just donate. The link's price went down. But if you were already familiar with the main ideas behind neural networks, backpropagation, and the ReLU activation function. Hello. Backpropagation is a really big word, but it's not a really big deal. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about Neural Networks Part 2, Backpropagation, Main Ideas. Note, this StatQuest assumes that you are already familiar with neural networks, the chain rule, and gradient descent. If not, check out the quests. The links are in the description below. In the StatQuest on Neural Networks Part 1, Inside the Black Box, we started with a simple dataset that showed whether or not different drug dosages were effective against a virus. The low and high dosages were not effective, but the medium dosage was effective. Then we talked about how a neural network like this one fits a green squiggle to this dataset. Remember, the neural network starts with identical activation functions, but using different weights and biases on the connections, it flips and stretches the activation functions into new shapes, which are then added together to get a squiggle that is shifted to fit the data. However, we did not talk about how to estimate the weights and biases. So let's talk about how backpropagation optimizes the weights and biases in this and other neural networks. Note, backpropagation is relatively simple, but there are a ton of details, so I've split it up into bite-sized pieces. In this part, we talk about the main ideas of backpropagation. 1. Using the chain rule to calculate derivatives. And 2. Plugging the derivatives into gradient descent to optimize parameters. In the next part, we'll talk about how the chain rule and gradient descent apply to multiple parameters simultaneously and introduce some fancy notation. Then we will go completely bonkers with the chain rule and show how to optimize all 7 parameters simultaneously in this neural network. Bam! First, so we can be clear about which specific weights we are talking about, let's give each one a name. We have W sub 1, W sub 2, W sub 3, and W sub 4. And let's name each bias. B sub 1, B sub 2, and B sub 3. Note, conceptually, backpropagation starts with the last parameter and works its way backwards to estimate all of the other parameters. However, we can discuss all of the main ideas behind backpropagation by just estimating the last bias, B sub 3. So, in order to start from the back, let's assume that we already have optimal values for all of the parameters, except for the last bias term, B sub 3. Note, throughout this and the next stat quests, I'll make the parameter values that have already been optimized green, and unoptimized parameters will be red. Also note, to keep the math simple, let's assume dosages go from 0 for low to 1 for high. Now, if we run dosages from 0 to 1 through the connection to the top node in the hidden layer, then we get the x-axis coordinates for the activation function that are all inside this red box. And when we plug the x-axis coordinates into the activation function, which, in this example, is the soft plus activation function, we get the corresponding y-axis coordinates and this blue curve. Then we multiply the y-axis coordinates on the blue curve by negative 1.22, and we get the final blue curve. Bam. Now, if we run dosages from 0 to 1 through the connection to the bottom node in the hidden layer, then we get x-axis coordinates inside this red box. Now we plug those x-axis coordinates into the activation function to get the corresponding y-axis coordinates for this orange curve. Now we multiply the y-axis coordinates on the orange curve by negative 2.3, and we end up with this final orange curve. Bam! Now we add the blue and orange curves together to get this green squiggle. Now we are ready to add the final bias, B sub 3, to the green squiggle. Because we don't yet know the optimal value for B sub 3, we have to give it an initial value. And because bias terms are frequently initialized to 0, we will set B sub 3 equal to 0. Now, adding 0 to all of the y-axis coordinates on the green squiggle leaves it right where it is. However, that means the green squiggle is pretty far from the data that we observed. We can quantify how good the green squiggle fits the data by calculating the sum of the squared residuals. A residual is the difference between the observed and predicted values. For example, this residual is the observed value, 0, minus the predicted value from the green squiggle, negative 2.6. This residual is the observed value, 1, minus the predicted value from the green squiggle, negative 1.61. Lastly, this residual is the observed value, 0, minus the predicted value from the green squiggle, negative 2.61. Now we square each residual and add them all together to get 20.4 for the sum of the squared residuals. So when B sub 3 equals 0, the sum of the squared residuals equals 20.4. And that corresponds to this location on this graph that has the sum of the squared residuals on the y-axis and the bias, B sub 3, on the x-axis. Now, if we increase B sub 3 to 1, then we would add 1 to the y-axis coordinates on the green squiggle, and shift the green squiggle up 1, and we end up with shorter residuals. When we do the math, the sum of the squared residuals equals 7.8. And that corresponds to this point on our graph. If we increase b sub 3 to 2, then the sum of the squared residuals equals 1.11, and if we increase b sub 3 to 3, then the sum of the squared residuals equals 0.46. And if we had time to plug in tons of values for b sub 3, we would get this pink curve. And we could find the lowest point, which corresponds to the value for b sub 3 that results in the lowest sum of the squared residuals, here. However, instead of plugging in tons of values to find the lowest point in the pink curve, we use gradient descent to find it relatively quickly. And that means we need to find the derivative of the sum of the squared residuals with respect to b sub 3. Now, remember, the sum of the squared residuals equals the first residual squared plus all of the other squared residuals. Now, because this equation takes up a lot of space, we can make it smaller by using summation notation. The Greek symbol, sigma, tells us to sum things together. And I is an index for the observed and predicted values that starts at 1. And the index goes from 1 to the number of values, n, which in this case is set to 3. So, when I equals 1, we're talking about the first residual. When I equals 2, we're talking about the second residual. And when I equals 3, we are talking about the third residual. Now let's talk a little bit more about the predicted values. Each predicted value comes from the green squiggle. And the green squiggle comes from the last part of the neural network. In other words, the green squiggle is the sum of the blue and orange curves plus b sub 3. Now remember, we want to use gradient descent to optimize b sub 3. And that means we need to take the derivative of the sum of the squared residuals with respect to b sub 3. And because the sum of the squared residuals are linked to b sub 3 by the predicted values, we can use comes from the green and the index goes from 1. So, when each predicted value comes from the green squiggle. And the green squiggle comes from the last part of the neural network. In other words, the green squiggle is the sum of the blue and orange curves plus b sub 3. Now remember, we want to use gradient descent to optimize b sub 3. And that means we need to take the derivative of the sum of the squared residuals with respect to b sub 3. And because the sum of the squared residuals are linked to b sub 3 by the predicted values, we can use the chain rule to solve for the derivative of the sum of the squared residuals with respect to b sub 3. The chain rule says that the derivative of the sum of the squared residuals with respect to b sub 3 is the derivative of the sum of the squared residuals with respect to the predicted values times the derivative of the predicted values with respect to b sub 3. Now, before we calculate the derivative of the sum of the squared residuals with respect to the predicted values, let's clean up our workspace and move these equations out of the way. Now we can solve for the derivative of the sum of the squared residuals with respect to the predicted values by first substituting in the equation, and then use the chain rule to move the square to the front, and then we multiply that by the derivative of the stuff inside the parentheses with respect to the predicted values, -1. Now we simplify by multiplying 2 by -1. And we have the derivative of the sum of the squared residuals with respect to the predicted values. So let's move that up here. And now we are done with the first part. Now let's solve for the second part, the derivative of the predicted values with respect to b sub 3. We start by plugging in the equation for the predicted values. Remember, the blue and orange curves were created before we got to b sub 3. So the derivative of the blue curve with respect to b sub 3 is 0, because the blue curve is independent of b sub 3. And the derivative of the orange curve with respect to b sub 3 is also 0. Lastly, the derivative of b sub 3 with respect to b sub 3 is 1. Now we just add everything up, and the derivative of the predicted values with respect to b sub 3 is 1. So we multiply the derivative of the sum of the squared residuals with respect to the predicted values by 1. Note, this times 1 part in the equation doesn't do anything, but I'm leaving it in to remind us that the derivative of the sum of the squared residuals with respect to b sub 3 consists of 2 parts. the derivative of the sum of the squared residuals with respect to the predicted values, and the derivative of the predicted values with respect to b sub 3. Bam! And at long last, we have the derivative of the sum of the squared residuals with respect to b sub 3. And that means we can plug this derivative into gradient descent to find the optimal value for b sub 3. So let's move this equation up and show how we can use this equation with gradient descent. Note, if you're not familiar with gradient descent, check out the quest. The link is in the description below. Anyway, first we expand the summation. Then we plug in the observed values and the values predicted by the green squiggle. Remember, we get the predicted values on the green squiggle by running the dosages through the neural network. Now we just do the math and get negative 15.7. And that corresponds to the slope for when b sub 3 equals 0. Now we plug the slope into the gradient descent equation for step size, and in this example, we'll set the learning rate to 0.1. And that means the step size is negative 1.57. Now we use the step size to calculate the new value for b sub 3 by plugging in the current value for b sub 3, 0, and the step size, negative 1.57. And the new value for b sub 3 is 1.57. Changing b sub 3 to 1.57 shifts the green squiggle up, and that shrinks the residuals. Now, plugging in the new predicted values and doing the math gives us negative 6.26, which corresponds to the slope when b sub 3 equals 1.57. Then we calculate the step size and the new value for b sub 3, which is 2.19. Changing b sub 3 to 2.19 shifts the green squiggle up further, and that shrinks the residuals even more. Now we just keep taking steps until the step size is close to 0. And because the step size is close to 0 when b sub 3 equals 2.61, we decide that 2.61 is the optimal value for b sub 3. Double bam! So the main ideas for backpropagation are that when a parameter is unknown, like b sub 3, we use the chain rule to calculate the derivative of the sum of the squared residuals with respect to the unknown parameter, which in this case was b sub 3. Then we initialize the unknown parameter with a number, and in this case we set b sub 3 equal to 0, and use gradient descent to optimize the unknown parameter. Triple bam! In the next stat quest, we'll show how these ideas can be used to optimize all of the parameters in a neural network. Now it's time for some shameless self-promotion. If you want to review statistics and machine learning offline, check out the StatQuest study guides at statquest.org. There's something for everyone. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you want to support StatQuest, consider contributing. Backpropagation is a really big word.
Transfer learning has become quite popular in the field of image classification and natural language processing. Here we take a pre-trained model and then we try to retrain it for the new problem. So if you remember from our data augmentation tutorial, we had flowers dataset where we are trying to classify 5 type of flowers. So in this video, we will use a mobile net pre-trained model from Google's TensorFlow hub, and we will use that pre-trained model to classify our flowers dataset. And you will see that previously it used to take many epochs to train the complete model and achieve high accuracy. In this case, using a pre-trained model, it takes only like 2 or 5 iteration or epochs to get a superb accuracy. So using transfer learning saves a lot of computation power, because many times these pre-trained models that you can get from places like TensorFlow Hub, they are trained on millions of images. If you try to train that model on your computer, it might take days or even months. But all you're doing is you're taking that pre-trained model, you're getting all the weights and everything, and then you kind of change only the last layer or last few layers for your new problem, and then you can get a superb high accuracy with this kind of approach. So let's get started. We'll go over some theory and then we'll do coding. This is Wikipedia's definition of transfer learning, which is you focus on storing knowledge gained while solving one problem and apply it to a different but related problem. For example, if you have a model that can recognize cars, it can be used to recognize trucks as well, because the basic features, for example, the tires, the steering wheel, and some of the components between cars and trucks will be still similar. So you can use this knowledge of this visual world to transfer that knowledge into solving a different problem. In today's coding problem, what we're going to do is we will take Google's trained mobile net v2 model, which is trained on 1.4 million images and total 1,000 classes. So this is a deep learning model that is trained at Google. It would have taken a long time and a lot of computational resources. You can see 1.54 million images is pretty huge data set. And the output is 1,000 classes. And these classes are a little diverse. You know, you have a goldfish, shark, some animals, then some hammerhead, military uniform. So you have, it's not just the animals, it's animals and some other objects, total 1,000 classes. And when this model is trained, it will have input layer, then some deep layers, and hidden layers in between. Then in the end, you have a softmax layer, which is just, you know, classifying it into 1,000 categories. In deep learning, what happens is we freeze all the layers except the last one. So, you know, all these layers that you see, we'll freeze it. And then we'll use this model to classify flowers, which could be one of the 5 flower types which I have shown here. And we are going to use same data set that we use in our data augmentation tutorial. So when you freeze this layer, what happens is the model weights don't change. So now when I'm performing my training, so by the way, you take the model and then you still have to perform the training. That's very important. But when you're performing a training, the weights in these frozen layers are not changing. So it almost, you know, looks like a equation. So you are having this one big nonlinear equation. So you're passing your flower, and this is a training phase. And then during using these weights, you will get a feature vector. You're almost doing a feature engineering. And then you use softmax to classify into 5 classes instead of 1,000. So I hope you get an idea that you're almost generating the feature vector using these frozen layers. So during the training, none of the weights, nothing changes, okay? And omitting the last layer is a very common approach. In some approaches, they also freeze only, let's say, 3 layers or 2 layers. And see, now these values are in between 0 and how do I know which class 9 is? Pilo library, so you can use this code.
Hello everyone and welcome back to the channel. In today's video we are going to run YOLO V8, which is faster and more accurate than YOLO V7. YOLO V8 is trained for object detection, image segmentation and image classification tasks. We will run all of these tasks in this tutorial. The timestamps are given in the description. Let's get started. First, we need to set up environment for YOLO V8 and install required libraries. I am using Anaconda, so let's open Anaconda prompt and create a new environment called YOLO V8 with Python version 3.9. Hit enter, press Y and hit enter again. Once the installation is done, activate YOLO V8 environment that we just created. Now install Ultralytics library by command pip install or down with will download torch available GPUs and one image here. Direct how type name repository trained on parameters JPG and the out have but notice that their confidences are very low. So we can add another parameter to the command conf equals 0.5, and now if we run it, only those with low confidence are gone. Now if you want to show the output in real time, you can set the parameter show equals and equals true predictions and bounding box information. You can set directory confidences printed on the border. This source if as well. As this is nano version, there are a lot of false positives. You can use any other larger model to get more accurate results. So now what if you want to run object detection on webcam? Well, you can set the source to 0 for internal webcam or RSTP address for your network webcam, or you can use some directory that have multiple images or videos to run object detection in just one go. So this implementation is really flexible. Now let's run image segmentation using YOLO V8. Let me delete this previous output folder. For image segmentation, we need to issue the following command: YOLO task equals segment, mode equals predict, and for model, we will use the name of segmentation model now. If we go to YOLO V8 official repository, there is this section for segmentation models. Let's say I want to run YOLO V8 Nano for segmentation. To get the file name, I'm going to copy this link address and paste it in a separate window. At the end, you will see this .pt file name. Just copy it and paste here in the command, and let's set the conf to 0.5. If we hit enter, this time the segmentation model will be downloaded automatically. Oops, I forgot to mention the source image. Let's add source equals 1.jpg to the command. And if we hit enter, the output will now be stored in runs and segmentation subdirectory. If we go there, we can see the predicted segmentation output. Again, just to get equals output to run the segmentation, and you can see object detection. For classification equals, I'm just and paste in the image for classification mention downloaded. If we open, these are fine, but the labels are inhuman. So tflight equals detect equals export. The adaptation will apply not online in initialized versions. Now the method equal file just true on the from model 1.0 name. To run YOLO V8 segmentation, just copy any segmentation model file name from the segmentation section and paste here.
Hi everyone, this is YML, and today's video is the first part of a series that I intend to create regarding object detection in computer vision and study the classical object detection architectures, starting with RCNN. The first thing that I would like to clarify at the very beginning is the definition of object detection. Well, you already probably know that machine learning systems, especially those based on deep learning techniques, are pretty damn good at classifying images. However, by going one step further, we may be interested not only in classifying what's in an image as a whole, but actually trying to find and draw boxes around the objects we are interested in. This task, known as object detection, helps us in better disambiguating what happens in a more complex image where there are multiple objects of interest, as is the case in the right image here, where an old lady is walking three dogs, which may be a pretty hard label to guess using a simple classification model. The question now is, how do you do that? The most naive solution we may think about is to have a sliding window that goes through our image and use a classification model that tells us whether the objects we are looking for are in that window or not. Unfortunately, this approach has a major drawback. It generates a lot of windows, and because the classification model has to run through each of them, it becomes extremely expensive and time consuming to use such an algorithm. Even worse, what do we do if our objects are too small or too big for the sliding window? Will the sliding window be able to capture the relevant objects in such a way that it does not confuse the classification model? If not, then we have to use multiple sliding windows of different sizes that lead to even more classifications, so even more computation power is required to run this algorithm. This may have worked in the past when classificators consisted of simple linear models, but in the deep learning era, this is not a feasible solution anymore. This is where the region-based convolutional neural network, or RCNN in short, steps in. The RCNN model is a deep learning model that improves the sliding window approach by introducing a clever algorithm called selective search that captures only a certain number of possible regions on which to run the classification model. In addition, it employs a deep retrained CNN model that acts as a feature extractor for a given region, feeding those extracted features to a SVM that classifies the presence of the object within that region. The selective search algorithm is designed in such a way to have a high recall but a low precision, meaning that out of the possible region it selects, many of them would be false positives that we don't really care about since they will most likely be rejected by the classifier. But on the other hand, it will barely miss a region that contains an object of interest to us. So, how does it work? It starts by oversegmenting the image using a graph-based segmentation method, creating some kind of C-segmentation, and then iteratively merges in a bottom-up approach the adjacent similar regions based on things like the color, the texture, the size, or the shape. Let's imagine that those are the regions and segments that the graph-based segmentation returns, the initial seed. We can clearly see that those regions are quite all over the place and none of them capture the objects of interest in the image. The person on the right and the TV screen sitting next to it. If we run the selective search algorithm for several iterations, we can see that a lot of those small neighboring regions and the point a region that contains an object of interest to us. So, how does it work? It starts by oversegmenting the image using a graph-based segmentation method, creating some kind of C-segmentation, and then iteratively merges in a bottom-up approach the adjacent similar regions based on things like the color, the texture, the size, or the shape. Let's imagine that those are the regions and segments that the graph-based segmentation returns, the initial seed. We can clearly see that those regions are quite all over the place and none of them capture the objects of interest in the image. The person on the right and the TV screen sitting next to it. If we run the selective search algorithm for several iterations, we can see that a lot of those small neighboring regions have been merged together and one of them even contains one of the objects of interest in the green box, the TV screen. If we run the selective search for even more iterations, then the number of returned regions diminishes even further and we are able to capture in one of them the other object of interest, the person sitting next to the TV screen. I won't go into more details regarding the selective search algorithm, but I've added some more resource RCNN architecture. The model uses the regions proposed by the selective algorithm or inference. For this click the like button and subscribe if you haven't already to be up to date with the new content. See you next time. Bye bye.
In CNN we might use for image classification. It actually is, and for object detection task we have to modify it a little bit. First, whenever they say object location, we have an input image. We defined what's so-called sliding window. At first, we just put it at the top left corner and tell it to classify the region. So it's an algorithm to propose us some regions. The algorithm CNN uses for that is called selective search, which has existed before. So given this image, the selective search might propose these bounding boxes that we can call them region proposals. One good thing about it is that it gives us like 2000 region proposal within 1 or 2 seconds. So now let's understand how the pipeline is like. First we have an image, then we run selective search and it generates some region proposals that, for the sake of simplicity, let's assume we have only 2 of them here. Next, we extract these region proposals from the original image, mark them to be all squared and suitable for a CNN module that receives them and produces a class describing which object is in the region. But is it enough? Actually not, because the bounding box generated by selective search algorithm is not precise. For example, here we can see that the sleeves of this person or ears of this horse is missing. So we add another branch that is responsible to tweak the bounding box a little bit and make it better. But how does this work? Our selective search algorithm gives us a region proposal described by px, py, ph, and pw. And our final output of our neural network generates a transform vector tx, ty, th, and tw. And our goal is to find these outputs described as bx, by, bh, and bw. Basically, it can be done using 2 operations. First one is called translation. It generates bx by moving the original px by pwtw. So if pwtw is negative, it moves it to the left, and if it is positive, it moves it to the right. Similarly, by is generated by moving py by phth. The other operation is called log space scale transform, and it rescales the width by multiplying the original pw and the exponential of tw. Why exponential? Because tw might be a negative value and we don't have any negative width. So this way we make sure it's always positive. And similarly, the height can be computed this way. Okay, we now know the general idea, but you might wonder, what if we output 2 boxes, both pointing to the same object? For solving this issue, non-maximum suppression, which is also called non-max suppression, is proposed. Note that, since it's a supervised learning task, we already know what the perfect bounding box is, and we manually label it before training the model, and we call it ground truth. And imagine our model gives us these 2 bounding boxes, both pointing to the same person. Our question here is, which one we should choose? Intuitively, the one that is closer to the ground truth and has more overlapping is a better candidate. So let's formalize this idea and use it to get the best option. The criterion we use to measure overlapping is called intersection over union. Let's first understand how this works by examining ground truth and this prediction. First, we compute the intersection, and let's imagine it's 12. Then we compute the union, and then we divide these 2 numbers. For the other prediction, we do the same computation, computing intersection, computing union, and dividing these 2 numbers. Now we have to decide which one is larger. The left IOU is 0.15, and the right one is 0.48. So we say the right one is having more overlap, and we choose this and remove the left one. Note, we use non-max suppression when the object is the same for all of the bounding boxes. To give you a better idea of what this means, let's imagine we have this image and these 2 bounding boxes. Even though they overlap, they are referring to different objects, and we shouldn't apply non-max suppression in this scenario. It's kind of weird to call this person an object, but yeah, this is how object detection treats people. The next thing we have to understand is how to evaluate our model. The metric proposed in the context of object detection is called mean average precision, or MAP. Let's imagine we have this beautiful dog picture. We already manually labeled these ground truth bounding boxes, and our model predicts these 3 bounding boxes. The question is, which predicted bounding boxes are correct? To answer this question, we take a look at their IOU. If larger than 0.5, we'll label them as correct, and otherwise, we'll label them as wrong. So by looking at these predicted bounding boxes, the second one is correct and the rest are wrong. The metrics we might ask here, and are quite easy, are what is precision and recall. Precision basically means, from all our predictions, how many of them are correct. Since we predicted 3 bounding boxes, and only one of them is correct, the precision would be 1/3. And recall means, from all the ground truths, how many are we predicted correctly. There are 2 ducks, and we only predicted one of them correctly, so recall is 1/2. Now let's understand how MAP works. It's a bit difficult compared to these metrics, so be prepared. First, let's imagine we have these 4 images and their corresponding ground truth. To calculate the MAP, we first take a look at only one class, and let's choose the dogs first. By giving these pictures to our model, first it predicts some bounding boxes, and each one gives us a probability of being dog existed in the area. The first step to calculate MAP is to sort these bounding boxes based on their probability score. And in the meantime, we consider a diagram called precision recall. Now we consider the left bounding box, which has the most probability score. Does it have an IOU more than 0.5? Probably yes, so we label it as correct. And we remove both the prediction and ground truth from the image, since we don't care about them anymore. Now, what's the precision? So far, we only considered one bounding box, and it was true. So it is 1 divided by 1, which is 1. And what is recall? We have total of 3 ground truth, and one of them is predicted correctly so far. So it is 1 divided by 3, which is 0.33. And finally, we draw our point on our precision recall diagram. Now let's consider the second bounding box. Does it have IOU of more than 0.5 with any ground truth? No, so it is incorrect. And we remove it from our image since we don't care about it anymore. The precision now would be 0.5 since half of our prediction is correct so far. But recall stays the same since still we only predicted 1/3 of our ground truths correctly. And again, we draw our result on the diagram. For the third bounding box, let's assume it has IOU larger than 0.5 and label it as correct. Now what's the precision? It is so the result after is with direction now, and this can give us and gives us, I'm afraid you to 50-59. It's a tough metric, but it's over. Actually, this video is over, and you now have the basic understanding of how our CNN works. In the next video,
Hey Nick, what's with the green box around your head?
What green box?
The one that's currently around your head.
They're on to me. Just kidding. If you want to be able to detect just about anything using TensorFlow object detection, this is the course for you.
What's happening, guys? My name's Nicholas Renat, and in this video, we're going to be going through the full-blown object detection course. So whatever object detection use case that you wanted to tackle, you'll be able to do it after going through this course. Now, we're specifically going to be going through 4 different use cases, so you'll be able to repurpose the code that we've actually got to be able to specifically detect the exact objects that you want to use. And it's all done using open source tools, mainly Python and TensorFlow object detection. Now, again, this could be used in a whole different range of use cases. So say, for example, you wanted to detect a person's face, or if you wanted to do sign language detection or face mask detection, this is the exact same code that you can use. Now, the nice thing about this as well is that we'll go through all of the setup, all of the installation, we'll show training, we'll also show exporting, which is a really big part of being able to build object detection models. So we'll be able to export this to the TensorFlow.js format as well as TF Lite. So if you wanted to run it as part of a web app, or if you wanted to even use it on a Raspberry Pi, you could. And we might just do that in one of our projects towards the end of the tutorial. So without further ado, ready to do it? Let's get to it.
Alrighty, what's happening, guys? Welcome to the object detection course. Now, this course is intended to take you from being a complete beginner when it comes to object detection all the way to being fully proficient and acting as a practitioner. Now, again, we're going to take this step by step so you'll be able to walk through at your own pace and be able to learn and leverage new technologies. So let's take a look as to what our actual game plan is for this. Now, there's going to be a bunch of stuff that we're going to go through. So ideally, this course is going to be fully comprehensive. So you're going to need you're going to have everything that you need to be able to get up and running. So there's 8 key parts that we're actually going to go through. And each of these key parts are pretty important when it comes to building object detection models. So first up, what we're going to do is we're going to install and set up everything that we need to be able to perform object detection on our local machine or PC. And in this case, we're going to be using the TensorFlow Object Detection API. And we're going to be doing that mainly using Python. Now, the reason that we're using the TensorFlow Object Detection API is that it has a whole bunch of additional capabilities that make it a whole heap easier to be able to build object detection models. So if you've ever looked at a real-time object detection architecture or model before, there is a bunch of stuff that you actually need to build in order to actually get one of these up and running. There's pre-processing steps, there's post-processing steps, there's visualization utilities. Now, again, if you're not familiar with any of these terms, don't fret. We're actually going to take a step-by-step and walk through each of those components. Just know that building this from scratch takes a lot of effort. So using TensorFlow Object Detection speeds this up a whole heap. So what we're going to do is we're going to install and set up the TensorFlow Object Detection API. Then what we're going to, alrighty, install and set up. So the first thing that I'm going to sort of show you is where to get the code. Oh, yeah, let's delete that. All right, that's my error. Again, there's going to be error stuff, breaks. So part 2 is, okay, then the next thing that we're going to be doing is setting up our folders. So right now we don't actually have anything created inside of our folder directory, right? So let's just add a navigation pane again. So if I go into our TensorFlow Object Detection repository, I don't have any folders here, but I'm actually going to set up a little folder directory that's actually going to serve us really, really well when it comes. So we've now gone through installing and importing our dependencies for image collection, defining the labels that we want to collect, as well as how to collect additional images for a particular class. And we've also gone and set capital L for long. Now, when I go to set up my labels later on, right, so you won't actually have that file created. Again, I'm going to just do thumbs down, change my label name, so it's going to be thumbs down, save. Now, if I step into my next image and come back, I'm going to have that annotation. Correct. You've also got a true negative.
Tuy nhiên thì trong cái việc đó thì cái nhắc là người ta ra là đi cái chuyện thì do là anh họ đang tập cho những người đang sinh hoạt ngày sau và làm những cái dạng là nhân dạng này cái sự như là những sự này thì không không có vậy để mình trả là được cái này nhưng không có cái cả cái cái nó cái xin là sẽ có bạn nó giúp đỡ cho những chỉ là đọc trình nó sẽ nó như là như là xem như là chuyện như là như là xem thì nó sẽ có hai độ hai vào cái hình ảnh và với nhau như mình phải phát đọc sau khi mình bắt đầu sau và khi giải thích như thế không với Excel và trong cái là một cái đó hai chi thì còn họ không giải được cho cái cả thì nó mà được không nó mà xử lý cái chuyện trong cái Yeah. Yeah.
Hello. So today I'm going to be talking about YOLO, which is a highly influential algorithm and framework used for real-time object detection, which means it has a very wide range of applications, including video surveillance, self-driving cars, face detection during the pandemic to measure temperatures and that kind of thing. So it's in short, it's a very popular algorithm that's been used a lot in the past several years. And the goal here is simply to create bounding boxes around the objects in an image, and then also to label these objects according to their class. Now, these sorts of object detection methods have been around for several years, but YOLO and its variants seem to capture a desirable mix between speed and accuracy. Now, the actual definition of mean average precision is a bit more subtle than that, but let's not worry about that for now. So as you can see, out of the models that are capable of what we can call real-time detection owing to their speed, YOLO seems to deliver the best performance, despite still being less accurate than some of the slower models. And the reason YOLO is able to achieve this is that it utilizes powerful deep learning architecture, while at the same time using the input image data in a highly efficient way. So just to compare with some prior developed models, the deformable parts model, or DPM, uses filters that represent whole objects. Objects and parts of objects to create a detection confidence map using a sliding window technique. And the idea here is that an object is likely present if all of its parts are present, even if they are configured in unusual ways. Now, region-based CNNs do kind of the same task, but differently. Here you have three separate models: a region proposal model, a CNN that extracts a feature vector, and a support vector machine for each class. Now, these three models, notably, are typically trained separately. And even though there have been many developments on the RNN approach since 2014, the essential idea of region proposal plus classification still applies. Now, the distinguishing feature of YOLO is that instead of looking at an image multiple times, whether it's to apply the deformable parts filters or to inspect the regions like the RCNN, you only look at the image once. So just to summarize how this scheme works, the first step is to overlay on an input image a grid with S grid cells on each axis. Each grid cell then produces two things. One, it produces a set of bounding boxes centered on a point inside the grid cell with associated confidence scores that an object exists inside each bounding box. And then it also produces a class probability map for each grid cell, which essentially tells what object class is most likely to be in that cell, given that an object in fact exists in the cell at all. And finally, it combines this information to yield the object detections. So, that's the abstracted framework, but how does it actually work in practice? Well, for each grid cell, we compute a set of output vectors. The first vector is a vector of class probabilities. The second is a set of bounding box parameters, specifying the x and y position of the center of the bounding box, as well as the square root of the width and the height of the box. And I'll explain why we take the square root a bit later. And then finally, we also have the confidence score denoting the model's confidence that an object in fact exists in the box. Now, instead of having just one bounding box, each grid cell will typically have multiple boxes, and this just allows the cell to detect more than one object. Now, in practice, instead of having several vectors, we just combine them into one big vector with length b times 5 plus n, where n is the number of object classes, b is the number of bounding boxes per grid cell. And in the original paper, the authors use a 7x7 grid with 2 bounding boxes per cell and 20 classes. So for each grid cell, we output a length 30 vector. But how exactly does this model just go from an input image to these output vectors? Well, simply, we just use a CNN, a convolutional neural network. Now, this architecture just consists of a stack of convolutional layers that distill an image into a more abstract representation, followed by 2 fully connected layers that transform this into an output vector for each grid cell. And the 3 channels in the input just represent the red, green, and blue channels in the image. Cool. So now that we have an idea of how the model works, let's look at how it is trained. Let's say we are trying to predict, say, this bounding box. Now the center of the bounding box is at this point here, so this grid cell will be responsible for it. Well, let's say we've predicted this green box here, along with the 5 parameters that define it: x, y location, the width, the height, and the confidence. And we want to somehow penalize the prediction because it isn't exactly the same as the ground truth. But what would the ground truth values be? Well, for the class probabilities, this is simply 1 for the correct class and 0 for everything else. Note that this assumes that the classes are mutually exclusive. And with later versions of YOLO, I think starting with YOLO version 3, the model is actually capable of multi-label classification, where 2 classes can exist simultaneously, such as dog and animal. But YOLO v1 just predicts 1 class. So that's cool. Now let's see how we calculate the coordinates of the ground truth and predicted boxes. Well, x and y are usually calculated with respect to the top left corner of each individual grid cell, and they are also expressed as a proportion of the total grid cell dimensions. Meanwhile, the width and the height are expressed as a proportion of the total image dimensions. Hence, these all fall into the 0 to 1 range. So just to take a quick example, let's say that the coordinates of the point are 16 and 44 pixels, respectively, from the top left origin of the entire image. Let's say each grid cell is 10 by 10 pixels, and the image has 7 grid cells on each axis. Then the x and y values are 0.6 and 0.4 respectively, where the percentage sign here is just the modulo operator. And the width and the height are obtained by dividing by 70. Yeah, well, so what about the confidence? Well, essentially with confidence, the question we're asking point is 10 by 10 pixel, just to, so, I think starting with YOLO version 3 class. Well, x and y are usually calculated with respect to the top left corner of each individual grid cell, and they are also expressed as a proportion of the total grid cell dimensions. Meanwhile, the width and the height are expressed as a proportion of the total image dimensions. Hence, these all fall into the 0 to 1 range. So just to take a quick example, let's say that the coordinates of the point are 16 and 44 pixels, respectively, from the top left origin of the entire image. Let's say each grid cell is 10 by 10 pixels, and the image has 7 grid cells on each axis. Then the x and y values are 0.6 and 0.4 respectively, where the percentage sign here is just the modulo operator. And the width and the height are obtained by dividing by 70. Yeah, well, so what about the confidence? Well, essentially with, so what about the confidence? Well, essentially with confidence, the question we're asking is, does an object appear in the grid cell or not? And confidence is the score attached to the positive answer of that question. So let's say that we have these ground truth bounding boxes with these center points and these grid cells responsible. Then in every grid cell except for those grid cells, the ground truth confidence is set to 0, because there isn't an object there. Meanwhile, in the green grid cells, the ground truth confidence is simply the intersection over union of the predicted and ground truth bounding boxes. Just to review what intersection over union means, the intersection between 2 sets, or 2 boxes in this case, is the area of the shared region. It's the middle figure here, while the union is the combined area of both of the boxes without double counting the overlap. So the intersection of a union of A and B is then simply the intersection divided by the union. So it's essentially a measure of the degree of overlap between 2 boxes or sets more generally. So the ground truth confidence is simply the IOU of the predicted and ground truth boxes. However, we know that each grid cell can produce multiple predicted boxes, so which one should we choose? Well, during training, in order to calculate the loss, we just use the predicted box that is the highest IOU with the true box. Incidentally, the authors of the original paper note that by assigning only one predicted box to each ground truth box, the different predictors are able to specialize and perform better on certain object classes or aspect ratios or whatever. Now, similarly, during inference, if we have 2 predictions, P1 and P2, then if the IOU between them is greater than some threshold, we only keep the one that is associated with the higher confidence in the presence of an object. Now, this whole process, called non-max suppression, just trims down the predicted boxes to prevent any overlaps between them. So, now that we know how all of the box parameters are calculated, let's see how they are used in the loss function. Now, the total loss function is basically just a sum of two terms, the object class loss, which operates on the class probabilities, and the localization loss, which operates on the bounding box parameters. And this is what the class loss looks like. So instead of using cross entropy or anything like that, we just take the sum squared error between the predicted and ground truth class probabilities, summed over all classes and all grid cells. Now, this interesting symbol here just means that we're only considering the class loss of a grid cell I if an object in fact exists within that grid cell. So recall the probability map that I showed earlier. Here there are plenty of cases where the model has predicted an object class where it's actually a background, and we're actually not counting those cases in the class loss. The class loss only deals with cases where an object has been mistaken for another object, and not where there is in fact a background. So what about the localization loss? Well, this is also split into a confidence loss and a box coordinate loss. The coordinate loss is summed over all grid cells and all bounding boxes in each grid cell, but it is only counted for those cases where cell I contains an object and box J is deemed responsible for that object. So here we sum the squared error of the x and y coordinates as well as the square root of the width and height. We also scale this entire thing according to a parameter, lambda chord, and I'll explain why this happens in a bit. Now, the confidence loss is a very similar form, except that the grid cells which do not contain an object are scaled by a parameter lambda no object, while those that do in fact contain an object are not scaled. And again, I'll explain why this happens in a bit. So here is the entire loss function. What's apparent is that we're just using squared error to obtain good values for the class probabilities and all of the bounding box parameters. So in this sense, object detection is just reduced to a regression problem. And this gives YOLO a sense of simplicity. So it really is just regressing all of these values here without anything fancy like cross entropy losses or anything like that. So from this, we know that YOLO works very well, but what are some of its limitations? And here I'm talking more specifically about the first version of YOLO. Well, first of all, of course, each cell can only contain one class. So or it can only predict one class, should I say. So if, say, one dog and one bicycle appear in the same grid cell, then this presents a problem. Moreover, each grid cell contains a finite, specified number of bounding boxes. So if very many objects appear in one grid cell, then this also presents a problem. One example is busy urban environments where there might be, multiple people in each grid cell. Now, the authors note some other limitations, which include the fact that bounding box prediction tends to struggle with unusual aspect ratios or configurations of object that it had not sufficiently seen in the training data. And furthermore, the loss function deals only with absolute values of x, y, w, and h, so it cannot deal with the fact that the same absolute error will matter more in a small box than in a large box. There is no explicit error scaling according to the size of the bounding boxes. But one method the authors developed to tackle this is to use the square root of the width and the height rather than just the width and the height. And this means that as the box size scales linearly, the square root of w and h scale sublinearly, which in effect suppresses differences between large and small boxes. And now the final consideration is that many cells do not in fact contain an image, and the consequences of this are twofold. In training, the confidence scores are liable to be pushed to 0, since this is the ground truth for most of the cells in an image. And furthermore, since the coordinate loss is calculated only for cells with objects, it will tend to be underrepresented in the final loss. So in order to address both of these problems, we can scale the no-object confidence scores, we can scale down the no-object confidence scores, and scale up the coordinate losses using the lambda scaling factors. And in the original paper, the authors set lambda no-object to 0.5 and lambda chord to 5. So, there we have it. YOLO is a fast and effective object detection framework that works because of its simplicity, using just a single CNN to learn the bounding.
In this tutorial, I want to show some finer details about what exactly the detection head is predicting for the bounding boxes. I am also assuming that you have gone over the previous tutorials in this series. This video will make more sense if you have done so. Here I am using the high level feature map of size 13 by 13, but all that I will explain will apply to other feature maps extracted from the backbone. In the current grid that I am showing here, there is a ground truth box for a pixel where the orange dot is. Let me zoom on it. In the previous tutorials, I had also introduced the notion of anchor boxes. For this cell where the orange dot is shown, the anchor boxes are shown in blue color. Here I have 3 anchor boxes, but if you recall, it's up to you to consider any number of anchor boxes for your grid cell. It depends on the setup of your neural network. There are 3 anchor boxes, but we are interested in only choosing one. And in order to do so, we need to select the most relevant anchor boxes. And this is where intersection over union, which is a metric that quantifies the similarity between the 2 bounding boxes, comes and play its role. Let's say that this is the anchor box for which we got the highest intersection over union. And hence this is the one that is associated with our ground truth box. So we have a ground truth box for a grid cell. We have the corresponding anchor box. And this is the point, the question we need to ask is, what exactly are we predicting? And one simple and straightforward way to think about is to maybe perhaps predict the delta or offsets that we would add to the anchor box coordinates. You can see the coordinates blinking. So you make your network predict the offsets that you will add such that the anchor box will end up aligning to your ground truth box. But there are certain issues with this seemingly simple formulation of our objective. And this is what was discussed in YOLO version 2 paper. The paper goes by the title YOLO 9000, but for all practical purposes, we call it YOLO V2. In this paper, they argued that directly predicting the offsets for anchor boxes lead to model instability, especially in early training iterations. Please note that this does not mean that the formulation is invalid. It's just that either it will take a long time for the network to converge or you need to employ some extra training tricks and strategies for it to converge. The authors rightly argued that predicting the offsets for anchor boxes is an unconstrained formulation. Unconstrained here means that the offsets that you will predict will take any value in the feature space. And this will result in the coordinates of anchor boxes all over the place in various iterations, various training iterations that you will go through. Let me read the sentence as it is very clearly stated in this paper. This formulation is unconstrained. So any anchor box can end up at any point in the image, regardless of what location predicted the box. With random initialization, the model takes a long time to stabilize to predict sensible offsets. You can see that they are also saying that it will take a little bit longer. The formulation is not invalid as such. And finally, they suggest a remedy. The solution they suggest is that instead of predicting the offsets, which would take your anchor box anywhere, and hence it is called an unconstrained, at least within this feature space it is unconstrained, why not predict the location coordinates relative to the location of the grid cell? Now this statement could be a bit cryptic, so let me explain it with the help of some visuals that might clarify the intention here. And for that we will first zoom out of this grid and we will see the entire feature map again. This is a high level feature map of size 13 by 13. Each cell that you see in this grid is 1 by 1. Area is 1. Which means that the grid cell with the orange dot is 5 units on the x-axis and 4 units on the y-axis. The starting coordinates are always top left of the feature map. You can see it like this as well. In other words, for a given grid cell, we know at least the x and y units from the top left corner. We have this information already. Let's bring the zoomed out version of the grid again. The x unit to the grid cell in the quotient is indicated using Cx and y unit to the grid cell is indicated using Cy. In our example, you can calculate Cx will be 5 and Cy will be 4. Just count the number of cells that you see. Now, what YOLO V2 paper is saying is that we predict the offset within our grid cell for both x and y units. Those are shown using the blue lines that I have shown. The paper labels them as Tx and Ty. This means that the final center for our bounding box coordinates will be Bx equals Cx plus Tx, By equals Cy plus Ty. Simple mathematics at this point of time. But there is an issue here. You see, the network is still going to predict the real number for Tx and Ty, and it could be anything. It's not going to be between 0 and 1. And you want that because you are predicting something within the grid cell and you know that the size of the grid cell is 1 by 1. So Tx should be or must be between 0 and 1.
Okay, this is the 5th chapter of the course where I'll be discussing object detection. Until now, in the previous chapters, we have seen the concepts of classical computer vision and also we have learned about convolutional neural networks. Before proceeding to object detection, let's revisit the definitions a bit. What is classification? You just look at an image and tell me what kind of object is there within the image. What is localization? You not only identify the object, but also you locate where exactly it is present within the image. The red box around this cat is called as the bounding box. Pictorially, you have to depict the location of this object using the bounding box. And what is object detection? If there are more than one objects in an image, then identifying and locating all of them is the case of object detection. For example, in this image, you have to locate these cats, this duck and the dog, and you have to draw the bounding box for all these objects. In this chapter, first I'll be beginning with the localization, then we'll proceed to object detection. Just to recap, in a convolutional neural network like VGGNet, AlexNet, etc., the convolution and pooling layers will act as feature extractors. The fully connected and softmax layers act as classifiers. If you compare this with the classical computer vision based techniques, the hog and sift act as feature extractors and SVM will act as classifier. So this is typically the classification pipeline in using a CNN. You have an image, you input through the convolution and pooling layers. These convolution and pooling layers will give you feature maps, stretch out the feature maps into one-dimensional vector and feed it to your classification layer which has fully connected layers. The last part will consist of one fully connected layer plus a softmax. This softmax takes the scores or outputs from the fully connected layer and converts them to probabilities. And depending on which class has the highest probability, you will conclude that this image has a cat. Taking the same thing, how do you modify the classification pipeline to do localization? That is, there is only one object in an image. How do you locate that object? And to do localization, we need a bounding box. We need to draw the bounding box around the object. And to draw a bounding box, you need 2 points. That is, if I have these 2 points, I can draw this rectangle. And a point is represented by the x and y coordinates. And so for 2 points, I need 4 numbers: x1, y1, x2, y2. Or there is another way of representing the bounding box. That is, you take the center of the box and also give the height and width. So you have x0, y0, h and w. So even in this case, you will need 4 numbers. In this chapter, for the ease of explanation, I will be taking this as an example. But practically in many papers, they use this concept to give the bounding box. So if you take this image as example, this will be your x1, y1, and this will be x2, y2. So the question is, how do you give out these numbers? It might appear very difficult, but actually if you look at the network in the last layer, it's very easy to do this. What does the last layer of your network consist of? If you expand this last layer, it will have one fully connected layer followed by softmax. What does this fully connected layer have? It will have scores for different classes. Let's say you have 10 classes in your network, like human, car, dog, etc. And for each of this class, you will have some score. For example, human might have a score of 10, 9, 2, then this will be 4, 3, -1, something. And for this class that is in this image, for example boat, the score might be very high, let's say 50. And what softmax does this, it will take these numbers and convert them to probabilities. Maybe for the boat the probability will be highest, say 0.95, and for all other classes the probability will be very close to 0. So that's how we know that it's a boat. Now with this knowledge, how do you modify the last fully connected layer to give you 4 numbers instead of 1? So basically what this fully connected layer is giving, it is giving you 1 score per class. For every class it will give 1 score. But what we need is, we need 4 scores. So we just need to modify the last fully connected layer as shown here. So I'll just modify it to give me 4 scores, which will correspond to x1, y1, x2, y2. So with these scores, now I can draw the bounding box. So I'll have one set of scores for each of these classes. Okay, but the question is, how will I teach the network to give me the correct bounding boxes? That is the coordinates of these bounding boxes. How will I teach the network to give me? For that, I can train the network using something called L2 loss. Let's see what it is. If you take this network, which is of dimension 600 by 800, this will be the coordinates of x1, y1, 200, 250, x2, y2 will be 600, 400. The same thing is shown here. And I will use these as the expected values. That is, my network should give out these values. So these are the expected values of x1, y1, x2, y2. We already know that your CNN, that is convolution and pooling layers, will give you some feature maps, which I expand to a one-dimensional vector. And in these vectors, at all the locations, I'll have some values, okay? And when I start the training, we know that the fully connected layers, all the weights will be initialized to values of 0.1 in all the fully connected layers. And please note that here I'll not be using any softmax because I don't need any probability scores here. I just need the actual values of x1, y1, x2, y2. So I'll not be using any softmax layer here. So this is how my network will look initially with all the weights initialized to 0.1. Now when I feed these values, the feature map values through this network with all the weights initialized to 0.1, I might get this value as output. Please note that these are just hypothetical values that I'm using for explanation. These are not real examples. So this value 0, 0, 800, 600 will correspond to these points 0, 0 and 800, 600, which will be this red box matching the dimensions of this image. Later I'll calculate the L2 loss. What is L2 loss? First of all, what is L1 loss? If you have two numbers, say 10 and 15, you just take the magnitude of the differences between these values, that is 10 minus 15 mod, you will get 5. Similarly, L2 loss will be nothing but you do 10 minus 15 and do the whole square. Because you are squaring, this is called L2 loss. And because you are not taking the square of these numbers, this is called L1 loss. Basically, this is the power of 1, this is the power of 2, something like that. So this is the prediction of my network, and I need to calculate the L2 loss. So I'll do 200 minus 0, 250 minus 0 whole square, then 600 minus 800 whole square, and so on and so forth. Once I have all these values, I'll just add it up. I'll get this as the loss, which is a very high value. Now what I will do, I'll back propagate all these losses through the fully connected layers. This time from 0.1 and so on, the weights will get updated to maybe 1, 2, minus 1, 4 and so on. So the same thing will happen in all the layers. So with these new weights now, the same feature map output, I'll take the dot product and forward propagate through the fully connected layers. This time with the new set of weights, this might be the output that my network gave. 100, 150, 700, 700 and 450, which will correspond to the orange box. Again, I'll calculate the loss and I'll back propagate the loss through the network, and the weights will get further updated. So some other changes will happen to these weights. With the new set of weights, this might be the network's prediction, corresponding to the green box. Here the loss is a very small value, just 250. And when I again back propagate this loss through the network, these weights will get updated with a very small value. Maybe 4 will become 4.5 and so on and so forth. And with this new set of weights, now I'll get the correct output corresponding to the yellow box here, which is matching with the ground truth. So this is how I will train the network to give me the correct bounding boxes. Initially it will output some random values, but I'll calculate the loss and back propagate through the network. I'll keep doing this until the network gives me the correct output. Once it gives, I'll just save these weights. So this way the network will remember to give correct bounding boxes for different objects. For example, if I train the network with lots and lots of images, then once the training is finished, whenever it sees the front view or back view of a car, what it will do is it will give the bounding box where the width is slightly higher than the height. But if it finds the car in a side view, it will give a bounding box where the width is very much larger than the height. On the same lines, if it looks at a person who is standing, it will give a bounding box where the height is much larger than the width. But if the same person is sitting, the height and width will be somewhat comparable. And on the same lines for different objects, if it looks at a monitor or TV, the bounding box which will be more squarish. So this way it will learn the properties for different objects. What kind of bounding boxes it has to give, what should be the relative dimensions. It will learn all these properties. And that is how the network will learn to give correct outputs for different kinds of objects. And also note that few other important points. Let's say if this is the image that I give as input to my network. Now that your network has learned the general properties of different objects, it knows somewhat that your car doesn't end here. Even though the rest of the car is not visible in this image, it knows that the dimension of car will stretch even further. So accordingly, it will take a guess and give me this bounding box. So this is very common when you are working practically with different images. So with this, you know that the network has become very intelligent, and even though it is not seeing the object completely, it can guess the dimensions of these objects. In this case, my network would have guessed that okay, the car will stretch up to this point. Okay, and even the height it will guess accordingly because the tires might stretch up to here. Also note that if a larger part of the car is visible in the image, then the accuracy of this bounding box will be more. For example, here it will guess that the width of the car is just 500 and the height is 300. But in this image, since more part of the car is visible, here it will guess that the width of the car is 600 and the height is 300. That is, this bounding box is more accurate compared to this one. So here we need to know two things, even if the object is not. Now combining is the dimensions of since these are generic, I don't need one. Let's say in my dataset I have three classes: person, boat and TV, and these are the outputs from my classifier. The fully connected and softmax layers will give me this confidence scores. And the same thing is depicted on the bounding box coordinates. And there is no, we know that I have a high confidence value. It will take these to X layers, will give you some. Some feature maps which I expand to a one-dimensional vector, and in these vectors at all the locations I'll have some L1 logs. The output from these outputs blank to do localization.
nói chung một con Minaro là con tổng đàn được đồng thì mình bất phải nó lương sức mình đâu có cần phải ở sự cần thế thì thế thì phải tích hợp và thì phải tích hợp cái đoạn web của bọn anh vào dính ở trong cái phần mềm của Insight và cái như thế thì cái đoạn này không biết là HSP tôi đồng ý để làm cái này để đi cái hướng của nó làm được cái tổng bài ấy nó không phải chỉ phải chủ đương cho cái đơn vị của mình để mình làm sau này nó sẽ có cái trang dashboard mà trước không có remote thì cái trang đấy nó không không phải là insight insight là chỉ đặt sự cho cái mình dùng nó còn sau này sẽ thành phần của nó cái thứ có các chuyên chỉ khác trong cái mình dùng thì nó sẽ không có insight cho nên thì nó phát triển song song hai cái đấy còn chuyện mà nếu mà đến chủ nó lên pro thì những cái tích hợp mấy thay vì agent phải sử dụng nhiều nhiều cái trang thì nó phải trao đổi với kế hoạch với IFC cho thể là nó có thể tích hợp vào được hay không còn tích hợp thì nó mất nhiều thời gian nên là để thay đổi gì nên là hai bên nó không kiến thức để tích hợp được vào thì sẽ đổi phát triển nó phải trao đổi với IFC như vậy. Bây giờ mình chiêu là mình phải để mai đây chuyện rất cho tổ lòng mình về ra bây giờ nó tối nó đang thực hiện là thì do mình rất thiếu nhiều cái sự gián đoạn nó chỉ là cái việc mình chuyển sang hết chuyển sang hết được kéo cứ phần này chắc phần là mai đây thì dự kiến là bọn em sẽ có cái phần đi sụt để kiểm tra cái việc vấn là nó không có cắn để thay thế nhưng không thì cái việc được sự phát triển cho một cái liên kết được sản mình sẽ làm ngay đây một liên kết sau đó một thời gian để chỉ để mình vẫn phải lưu giữ cái vuông để mà được để kỹ sau khi mà nó qua một cái khoảng thời gian mà mình cái phần để cái tai vuông nữa thì cái đấy của mình bắt đầu là gọi là đi connect lại cái sẽ đến nguyên để mình để kỹ để mình cài cài cái lá basic của đấy sau đó là để mai đây mình giao đầu thằng người bằng nốt đó có biết sao nhưng mà truyền tải về dữ liệu từ mình có truyền tải truy cập đến dữ liệu xí như thế không thì chắc nào để chỗ nào để bọn nó tính toán lại thôi truyền tải nó sẽ thành nguyên đi chuột cái phần mà có tôi đến đêm thì nó việc khá lâu chưa mà nó đang chuẩn hết rồi thì mình do là năm tôi sẽ có việc sẽ không ok cái này để mình kết hợp với tôi cho của nó tăng khu vực với cái link để kết với chỉ có không có năm năm có bảy và đúng không Yeah, okay. Chúng ta muốn đây là Itu tinggal.
So what's come right here? Go to the
Done. Two. Yeah.
chạy đâu chạy nhanh. Thôi thôi.
Vậy thì FTC nó phát của chị em phát triển vâng những cái được cái việc học em độ hoàn biết hết cái cuộc thì ngoại cảm đi của các sinh làm hay rất là nhiều đâu khi nhiều người em thì cái nhiều em và cái ông em đặt tiền ở này thằng em người xoay đấy chỉ là cái thứ em thấy nhất khi mà cuộc số thì ông nó chính không bị kích luôn chỉ gọi vào là kích để em ơi và thì mình gặp máy hát máy luôn để em xem là đi đường nào thì em bắt cho nó chính xác cái phần bị trước con số 35 nhé. Thì chắc là để em tập lốc một tí nhé để hai chút anh đi bao nhiêu cả nhân phát là cái ai kiểu như sao thì hot anh đi là hot sang năm
Anh hay
và học anh đây là em như em đặt ở đoạn này các cái sim thì bắt thì dùng ngoài từ phía khách hàng từ ngân sách ở khi đó đó sẽ mình sẽ chỉ dùng có cái em bắt đầu nói đi từ phía dưới đó còn anh sẽ để cho anh con đấy còn anh sẽ bắt đầu nói các sim đặt cái giao thông còn nó sẽ đặt đầu đi khách hàng anh nhắc á và sau rồi mình tay lại thì đeo cái gân thì hoàn toàn cái việc đó thì mong là tầm cho thì vẫn đang có cuộc sống chị thà tăng gần của chị sẽ là bắt 2-3 đầu đây đại học cho cái lên mình search khoảng và cho sang tiền đó mình thì mình bắt đầu tiền bắt đầu lên lên Sẽ test tại vì là rất là mình test thì mình nghĩ thì là từ bắt đầu mình chắc là mình test khoảng mình lắp ra cái mình mục đích là mình xem là cái bắt đầu nó có khi mình mất dây hoặc là nó bắt thì bắt được cái nó chỉ mình khá hay hơn mình chỉ lắp thôi là cái cái không 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 em thứ bảy em thứ bảy của ông chúng tôi dừng lúc nữa tại vì em không thấy nó để con vâng ạ em sẽ đặt con nha bây giờ mình có biết gì lên ý định snap vào chị Hà ngắt đi chưa nhưng em cũng rất là bắt đầu như thầy gốc đó thầy gốc là đầu em đi lại đâu phải anh nhân tưởng như anh có thể nó sở cái đây rất tất cả những cái mà quay cho mấy cái hạt để được anh tế vâng mình với cao còn em tác trò đó thì em biết còn là bắt từ tại vì là tức là cái ghi nhận thì chị không phải nhưng mà chị phải ghi nhận thì lại là mình mất thì nó có cái cuộc nào thì trong cái để em tắt trở lại các còn mình ra quay lại thì lại không đi về để test những cái cuộc gọi thì không đi để test một cuộc nữa tiếp theo không có bị như thế không đấy alo Không biết là nó lắp tiếp được không? Hoặc là không. Nhưng em chỉ như từng đó. Còn cái tình đó có một rồi để không các cái được một cái hoạt động một cái tại vì em xem có mất rồi không thì cắt được phần đầu của nó thì chỉ đơn giản lắm. Anh nhân chỉ chuyện này như chỉ có không là chú tép mà cho nên là cái chung chúng ta cần anh cách số anh bắt số anh đi vâng có bắt kiểu anh em bảo được chứ một tuần rồi cái đó thì là anh cũng sẽ hiểu luôn nhưng mà là khách hàng một tuần một cái nữa thì mình thì đáp phải em mở xong gọi test thì cô thì anh sẽ bắt thì hôm nay nó bắt một xíu càng kiểu NPC khi như vậy anh gọi những người rất là và bạn xong bắt luôn thì mình rất là không làm rồi anh hát anh rất là cái này của bạn khi rồi theo không thì mình step được thì chúng ta cần đó Được bắt. Được bắt. Em gửi một cái phòng. Được rồi, được một tiếng. Như có bắt hả? Có. Cái bắt lên đấy. Được. Bắt ra được không? Được trong này. Được trong cái thời gian thì giờ thì mình là được đóng thì sẽ còn bây giờ cái câu là đóng thì mình thì bắt được nhiều con người đồng thì anh thì bắt được có thì chúng mới học có được mình học mình sẽ học có các đào tạo thì
In this video, we'll look into RCNN, which is short for Regions with CNN Features. And this will be the first video in the object detection series. The plan for this series will be to go through all the seminal works in object detection in the past decade, all the way from RCNN to YOLO V8. For all of them, we'll try to understand every detail of the method, and for some of them, we'll also follow up with an implementation from scratch. And the first one that we'll be starting with is RCNN. But before we look closely into RCNN, let's look at the object detection task first and see how it's different from other common tasks of vision. Let's start with the task of image classification, where the goal is to assign a class label to an image from a set of class categories defined in our dataset. These labels could also be multiple classes for an image, but for now, let's stick to single class label. Then there is the task of image localization, which demands a little bit more from us. It requires us to locate the instance of an object category in an image using a tight box centered on the instance. So essentially classification with single label plus locate the object. Now on to object detection, which further demands more. It requires us to locate all instances of all object classes in an image. And these classes, just like classification, come from a predefined set of categories present in our dataset. Let's also take a peek at these three from the architecture side as well. And for classification, again, let's stick to singular object of interest. We will typically have some CNN, and after the feature maps, some FC layers, and the last layer generates the classification scores for all categories present in our dataset. And we'll use cross-entropy loss to train it. For localization, we still need everything that we had for classification, except now we also need to predict this box, which we usually do via different set of FC layers. For the box, our goal is to predict a very tight one around the object, such that it should cover the entirety of the object while keeping the box area as minimum as possible. So a box like this is not preferred because we are not covering the entire object, and a box like this is also not preferred because we are including regions of the image which we don't really need to. Also, in most cases, we predict axis aligned boxes, but there are some implementations that we'll see later on where we can predict boxes with arbitrary orientation. However, let's focus only on axis aligned ones for now. There are typically two ways to define these boxes. You could define it using the coordinates of the top left corner of this box, which is x1, y1, and the coordinates for the bottom right corner, x2, y2. Another way is that we use the xy coordinates of the center of the box and the width and the height of the box. Both of these can easily be converted to the other using this relation. And the values can either be pixel coordinates, so if your image width is 256, then x1 values can range from 0 to 256, or scale coordinates, so you could have x1 range from 0 to 1, where you are scaling the coordinates by dividing it by 256. Okay, back to localization. So our FC layers in localization task will predict these box coordinates in addition to the classification scores, and they can be trained using something like MSE. For detection, we want to predict boxes for all instances of objects together with their respective classes. Let's just assume we are interested in predicting person and cars. Now you have to predict this person, but there could be another person here, and another person here. And as part of object detection, you have to predict all these three. Building up from image classification task, one way to solve this would be to scan the entire image using windows of same size as this person. And for each window, we take the image crop belonging to that window and have our classification CNN say if this image crop belongs to a class that we are interested in or it's a background class. And after training this CNN, when a crop like this would be fed to it, it would predict with high confidence that it's a person class. So it's similar to a classification task, except rather than training the model on dataset images, we train it on these crops of our dataset images. But the same person could also be here or here, and you want to detect them as well. And while detecting, you again want to have a tight box. To achieve this, you would have to start taking crops of different sizes. Or you can take the same window size, but start taking crops from downscaled version of images as well. Which means that crops from higher scale images would allow you to detect smaller size objects, and crops from downscaled images would allow you to detect larger objects. But whether you scale boxes or scale the image, some component of scale will be there to increase the number of boxes that you need to handle for one single image. Now to detect these cars, you need slightly different square-shaped crops. And to print drawing this huge number of crops will be a lot. You can reduce this by having your windows take strides greater than 1, but that cost still handles this task. As of now, we have a lot of window crops and a deep network which will take these crops and predict a class label for them. And the problem that we are facing with this approach is that since we end up with too many crops, we would have ended up reducing the computation cost without any trade-off in terms of accuracy of detection. RCNN follows this approach. Instead of using all the window crops, it offloads the task of finding out regions of image which possibly contain an object to some other method. This method would then propose certain regions in the image which it thinks could possibly contain an object, and then we would do all the computations from here on forward only on these region proposals.
Lo một cái nó đều là con rồi ví dụ như là mình đặt con tôi là chưa đúng lúc thì mình cần phải đặt sức để cho tụi con đặt được ra thì mình đặt sáng thì mình cái mình là cái gì rồi đấy nhưng mà rồi nhưng mà rồi cái cái này cái lần
This video engine image for computer vision such as object detection, recognition, and identification. A non-directed graph G is defined for image, where V is pixel partitions and E is edges between two adjacent pixels. Each pixel connects to its 8 neighboring pixels, and each edge determines the similarity between two adjacent pixels. Exhaustive search groups the similar pixels to form initial distributions. For selecting the search method to generate the region hypothesis that probably contain object in image. Selective search uses the four similarities to measure if two regions are merged as a single region. First, color similarity is defined to measure color similarity between two regions, Ri and Rj. Each region uses a total 75 bins of CI for RGB images. The color similarity is defined as histogram intersection, as here. Histogram of the merged region is computed by using this formulation. Size of the merged region is equal to sum of two regions. Size Rj and size Rj. Texture similarity uses a skew invariant feature transform to represent texture of a region. Gaussian derivatives in 8 orientations using sigma 1 use for each color channel. Each region is represented by a texture histogram Ti for RGB images. Texture similarity is represented as a histogram intersection, as here. Size similarity encourages small regions to merge early, so that object locations at all scales are created at all parts of the image and prevents a single region from gobbling up all other regions one by one. Size similarity of the IM shape compatibility measures regions Ri and Rj to fit to each other. If a region Ri is contained in Rj, they should be merged to avoid holes. Suppose that BBIG is a bounding box that contains regions Ri and Rj. S field is a fraction of an image. S is a weighted sum. That's right. Indicate instances. Thank you.
The method that RCNN uses for this is selective search, and that's what we will look into next. Step into regions. Step 2, hierarchy of regions to be a graph with vertices being each of the pixels and edges indicating neighborhood of each pixels. And each edge has a weight measured by some sort of distance. It could be color difference, texture difference, or a combination of them, or some other metric which captures this distance. So then maybe these nodes of being similar texture and color will be connected by an edge with a small weight, and maybe these two, because of say color difference, would have an edge of larger weight. At the start of segmentation, every node is a component by itself, and then we pick the two components with the smallest edge weight. And if the weight of the edge is less than some predefined threshold, we merge those two. The merged components now become one singular component. We keep on repeating this till there are no components that can be merged, because all the edge weights between components are larger than our threshold. There are quite a few implementation details here, like how do you define edge weight, how you define neighborhood, what's the threshold criteria of merging two components, especially if there are multiple pixels present in that component, and so on. If you really want to understand all those technical details, I would suggest to check out the link that's mentioned in the description. But this graph segmentation is ultimately to partition the other in two nodes in the same component. Should touch on our box, you'll notice that these miss larger. Running the first step of selective search on our image gives us this result. Now if you start wrapping each region with a box, you'll notice that these miss larger objects. Like look at the person segmentation. This is where the second step of selective search kicks in. Essentially, what this step does is it starts combining smaller and similar regions into larger regions until only one large region remains, giving us a hierarchy of regions. And all these regions can then be bounded with boxes to give us a set of region proposals, capturing objects of small as well as large size. This merging of similar regions requires a notion of similarity, and for this, selective search uses multiple facets. Color similarity, which will make regions of this t-shirt the person is wearing similar to each other. Texture similarity, which maybe will make regions belonging to the trees more similar as they also have same color. Size similarity, which captures that two smaller regions are more similar to each other than two larger regions. This ensures that the merge of two smaller regions happens first. And finally, shape similarity, which is a measure of how well two regions fit into each other. This ensures that nearby regions are merged first rather than far off. So if you have a region 2A is present in, we merge smaller regions, we could get an output looking like this, where you can see first regions of trees are being merged, and as the merging progresses, we get larger and larger regions. Merged now, the high similarity, where you can see first regions of trees are being merged, and as the merging progresses, we get larger and larger regions. These four similarity measures can be combined using different weights to give different strategies of merging. And you could also do this on the same image, but using different color spaces. By changing implementation, we fetch the segment, the select set of, here is for clarity, as the method actually returns close to 1600 proposals for this image. Proposals, which we have already seen and represented work, AlexNet, on a large dataset for the image classification task. After this, we take the network and remove the last classification layer, and now add a new classification layer which caters to classes present in our detection dataset. So if we have two classes, person and car, our final classifier layer will have two output units, plus another one for background. We are going to fine-tune this entire network on the task of classifying region proposals into the appropriate class. But in order to be able to do that, two things need to be considered. First, AlexNet network accepts input to be of shape 227 x 227, but our region proposals can be of any arbitrary shape. And second, in order to train this, we need to set the ground truth label for every proposal. For some proposals, it's easy. Like here, one is car and one is background. But what about this one? Or this one? Do we label it as a car or do we label it as background? Let's tackle the shape problem first. The authors do a simple resize transformation for this with some additional details. So given these proposals, we can convert them to our desired size. End, we still get 227 pixels, has exactly p pixels of context present in it. And in implementation, a value of 16 pixels is used for p. For cases where this additional context is not present, like if the box is already at the extreme boundary, in these cases they use a padding of mean image pixels instead. The authors experimented with few other approaches. Now, common metric of intersection divide will be from 0 when there is no overlap to 1 when two boxes exactly overlap. And here are different box positions to give you a feel of how different IOU values look like. Now our dataset will have images where we know the ground truth box locations. And for this image, let's assume we only have two ground truth boxes. And these are the 1600 region proposals that selective search will return. For considering which of these are positive proposals, that is proposals belonging to non-background class, we select those proposals which have an IOU greater than 0.5 with any ground truth box. This gives us these. And everything else, that is all proposals which have an IOU greater than 0.5 with any ground truth box. This gives us these. And everything else, that is all proposals which do not have enough overlap with any ground truth box, become our background class proposals. Then to fine-tune the network on the classification task, during training, we randomly sample a number of positive proposals and a number of background proposals. And this becomes our batch. And remember, all of this will be resized to 2 to 7 to ground truth. And for this image, let's assume we only have 2 ground truth boxes. And these are, let's assume we only have 2 ground truth boxes. And these background 0.5 any ground, then to find the number, this becomes our batch. And remember, all of this will be resized to 2 to 7 cross 2 to 7. Using this, we pass and train the entire network using cross entropy laws. There is one other aspect which we need to consider here, which is, what if we have 2 ground truth boxes with which a proposal overlaps? So let's say this image, and these 2 are ground truth boxes. Then with this proposal, and here assume it has greater than 0.5 overlap with both the ground truth boxes. Then we'll obviously select this as a positive proposal, but the class associated with it will be the class of the ground truth box that has higher overlap with the proposal. So here, if that's the mirror, then this positive proposal will have a ground truth class label of mirror. This entire fine-tuning is beneficial even if all classes are common between our detection dataset and ImageNet. Because up until now, the network would have not seen these warped images. So fine-tuning allows the network to improve its ability to recognize these warped images as well. After this training, we have a network that does the classification of region proposals into background or some class present in our dataset. Then we throw off this classification layer again and now use the FC layer's output as the feature representation of proposals. As the final step, we now train a linear SVM for each class, which takes this feature representation and learns to classify whether it's a positive instance of that class or negative instance. If you know SVMs, great, but if you don't, then just think of this as a linear classifier, learning a decision boundary in the 4096 dimensional space. So the person class SVM is going to learn to use these features to classify the proposal as person or not person. Note that the deep network is not updated and is frozen during this stage. Here also, we need to understand how do we find whether a proposal is positive or negative for this class. Unlike previous step, here the authors do it a bit differently. For labeling the ground truth for training class K SVM, The positive label is only assigned to the actual ground truth box with label k, and negative label is assigned to proposal boxes with less than 0.3 overlap with all ground truth instances of class k. Also, this SVM is trained with hard negative mining, which essentially just means that you give more priority to examples that the network is finding hard to classify correctly, rather than those that are easy for it. So here it could be that the network finds it hard to classify proposals with greater than 0 but less than 0.3 overlap as negative instances. To compare this with the earlier step, in fine-tuning stage, we used a threshold of 0.5 and did not ignore any proposals, whereas in SVM, proposals with IOU greater than 0.3 are ignored. Just to illustrate this difference further, for this image, and let's focus only on person class as of now, so this will be our ground truth box. And these were all the selective search returned proposals. During fine-tuning, these were the positive labeled proposals for person class, and these are a sample of background proposals, as in those with less than 0.5 overlap. Here I have removed all negative proposals which have 0 overlap just for clarity. For SVM, this is the only guy with positive label, and these are all the negative proposals with less than 0.3 overlap. Again, here I have removed those with 0 overlap. We'll soon get into reasons for this difference, but if we had to summarize everything that we have done till now, then first we trained a CNN on ImageNet, fine-tuned this CNN with resized proposal on the detection classes, and this was our definition for getting proposals with labels as non-background and background classes. Then we train a SVM for each class to use this learned feature representation and classify proposals as positive for class K or negative for class K. And now this was our definition of getting the labels. So there are two things that could be a bit unclear at this point. Why have these different definitions of ground truth labels during fine-tuning stage and SVM? And second, why even have this SVM step? At step 2, after fine-tuning, we have a network that, given a region proposal, can classify it as a category that we are interested in or background. Then why not leave it there and call that as RCNN? The authors give details of this in the appendix of the paper. They mention that rather than having the 3 steps, like we have seen up till now, they first just had SVM trained on the feature representation of proposals by a network trained only on ImageNet, so no fine-tuning. And at that point, for SVM, this definition of positive and negative labels with 0.3 threshold ended up being the best on validation set. Then when they added the fine-tuning stage, at start, they had the same definition of positive and background, but that gave worse results compared to the definitions that they ended up using. They believe that it's because of the limited data present during fine-tuning. Specifically, based on the SVM definition of positives, for this image, we would only get one positive proposal. But if we use the greater than 0.5 threshold, we would get a higher number of proposals that the network sees as positives. They feel this increase in positive examples is important to fine-tune the entire CNN and prevent overfitting at that stage. Then comes the second question, that okay, so why not skip SVM? And again, the authors mention that they tried that as well, but it also ended up giving worse results. So during fine-tuning, the network would see all these as positive instances for class person. This does not allow precise localization, and the network would treat all these images as same, which might not even lead to the best discriminative capability. Like as a hypothetical example, it could be the case that the network just discriminates person and non-person using presence of hands. Then both these proposals during inference time would actually be the same for the network. In contrast, the SVM would only see this as the positive for person class. Now you could argue that just by this also, there is a possibility that the network uses the same discriminating criteria as before. But remember, SVM is also trained using hard negative mining. So
Tuy nhiên có cái sau hoạt này thì có quan trọng là mình được đâu cái coi là những cái về anh nghĩ là có suy nghĩ là thì nó sẽ sau cái nghĩ có nó suy mong hơn cái việc là nó suy mong đến đấy thì nó đâu nó không đâu là cái gì thì sự nó sẽ bị dần nhau và là cái sau là cái mắt tao thì nó sẽ đó thì nó nhưng khi ngay đầu đây là ai hay là khách nào dạ rồi di động em lại phản ánh khi nghe được nó mà đầu NPC nhận nghe được cái gì nó sinh gọi của NPC lên được đặt được vào đó là tương bạn cái trên chuyên như sao và trong quan hệ cái tin đa thì các bạn nghĩa các bạn thành vô vàn chưa đang bị từ NPC lên cái phô lên phải thì đó là NPC thì nó lại rõ người rồi kia khi nghe để nó mình bao bắt ăn để làm bắt tay rồi chỉ nó và những suy nghĩ như thế thì họ bình thường mình thấy nhất là nó trên lớp đấy thì so nó bằng thời gian đầu tiên thì nó bắt đầu nói thì nó vẫn nói thì là nó nói như thế rất là nó nhận ra thì đồng ta này cho nó gọi là một cái đấy thì nó không nói được đấy nó sợ cho tình đời thì cái này nhưng mà cái gì mà nó là cái không sức khi hiểu tin nó chỉ kêu nó như nhau anh chị phải là cái gì thì cái này là như thế nó chỉ được tiền là chuyên tâm không cái là sao thì đéo là bài tập cho đàn như vậy kiểu xong rồi bằng nó trong nó thì bắt tay thế thì mình phải tập cho nó đã phản hồi như thế thì tôi sẽ nhận hai cháu như là đơn sở thì cái điều học thích đó đó thì đi tham tôi thì nếu là phải đến cho ban đầu thì rất sớm
So assuming the hard negatives to be proposals with something like or background. But we are still at the mercy of the kind of proposals that we get from selective search. So if one of the regions that we get is this, we are in a great position to predict an accurate box. But if this is the best proposal that we get, then there is really nothing that we can do. We have to live with this localization error in our predicted box. To reduce these localization errors and make the predicted proposal box more tightly fit the object, the authors add another component to RCNN. This is called class-specific bounding box regressor, and it is really just a linear regression model that uses the selective search proposed region coordinates and transforms them into new box coordinates. Let's see how we do that. Assume we have this proposed box. Then we use the coordinates of this box to get these four values, which is the xy coordinate of the center of proposal box and its width and height. We do a similar thing for the ground truth box and get these four values. The authors then parameterize the transformation from P to G in this fashion, where these are the parameters of transformation. We can rewrite this, and now these values are the targets that our linear regression model is going to learn to predict. For training this model, the authors take the pooling layer features for a proposal and feed it through linear layers, and train these using MSE and regularization to predict the transform with the best truth box. For this, the authors assign each proposal to the ground truth box with which it has maximum overlap, but only if the overlap is greater than 0.6, which they reach using validation. Otherwise, that proposal box is not even used for training the regressor. Again, remember this process of training bounding box regressors is done for each class, and we get class-specific bounding box regressors. After all the different stages of RCNN, when we see the detection outputs for this image, and here let's add another person. So for this image, when we see the detection outputs, we would get something like this. All these boxes are good predictions because they do contain a valid object within them. But because of the large number of proposals and the bounding box regressor, we would see multiple detection predictions for the same object. But we don't want that. We want one box per unique object. So we apply NMS, or non-maximum suppression, which is common in object detection, and it just aims to suppress or filter out redundant boxes. Let's see how it works. These are all our predicted boxes prior to NMS. We first separate prediction instances by class because NMS is going to be performed separately for each class. We then use some measure to estimate the quality of box, which is the confidence score. And here we'll use the predicted class probability as the confidence score. So the output of our SVM. Let's just put in some random values. Then for each class, we sort the instances based on this confidence score. And now we start building our actual predicted box list. Let's do first for the person class. We select the highest confidence box and filter out all boxes that have high overlap with this box. And because of sorting, they'll obviously have lower confidence. The overlap here will again be computed using IOU. And let's say we use a threshold of 0.5. So all these boxes will be removed. These two still remain because of their overlap being 0. Now again we pick the highest confidence box from the remaining predictions. And repeat by removing all boxes which have high overlap with this one. Which means for person class, we output just these two detections. We do the same for the car class. We pick the highest confidence box and remove all which have high overlap. Here, every other box will have high overlap with this one, and hence all of them will be removed. This is how NMS will reduce the redundancy in the box predictions, and we would finally output just 3 detection boxes for this image. Let's now look at the results the authors end up achieving with RCNN. The typical metric we use in object detection is MAP, which is short for mean average precision. I had earlier thought of talking about MAP in this video itself, but it would have made this video much longer since I wanted to cover MAP in detail. So I'll do it in the next video. If you know about MAP, great, but for now we'll just use the word accuracy instead. So if you don't know about MAP, it's fine. Hopefully after the next video, you will have a complete understanding of it. But know that wherever I use accuracy, I mean MAP. And higher the MAP is, the better performance it represents. Let's look at all the steps of RCNN and how the accuracy changes with those steps. The first result that the authors provide is without the fine-tuning step. So we train a CNN on ImageNet, get feature representation of proposals returned by selective search, and then train a SVM on this representation and post that NMS. This gives us an accuracy of 44.7, and this is on VOC 2007 test set. After adding the fine-tuning stage, the accuracy bumps up to 54.2, where now we fine-tune the CNN on the resized proposals and the classes that are present in the detection dataset. Then after adding the class-specific bounding box regressor, the accuracy further jumps by 4% to 58.5. And finally, instead of using AlexNet, the authors experiment using VGG, which has higher accuracy on ImageNet but also higher parameters. This further bumps up the accuracy to 66, but this also comes up with a trade-off of higher compute time. When you compare RCNN results with other previous methods, you will see that there is significant improvement in terms of detection accuracy that RCNN is able to achieve. So this was all the important aspects of RCNN that I wanted to cover in this video. Hopefully you got some basic understanding of it and even object detection in general. In the next video, we are going to talk about MAP and look at its implementation, and even look at an implementation of IOU and NMS. And post that, we'll get get into fast and faster RCNN. We'll only be implementing faster RCNN out of these three, since that is the one that's commonly used. Thank you so much for watching this video right till the end, and hope you have an amazing day.
Today, we are diving into the world of face detection using YOLO V8, one of the powerhouse of object. Excited about this tutorial? Kindly give me a thumbs dirty and write some code. But before we get started with the code, the files, we are not going to waste time in the description where you can download this model. So you have to scroll down, and at the down here, we have several face detection model. We have the
Có đẩy sinh tại thành mail thành ra gần vậy. Là ý thức đáng lẽ là cái việc mình chỉ đặt lệnh thôi, bạn cái đấy chúng ta đều thể tạo được.
Make sure your Fulbright's off because it's like supposed to be kind of scary.
Okay,
Just
yeah,
letting
it
you
is,
know.
it is.
I mean, I'll follow you, but
Oh, is
I
it
won't
standing?
really do anything. No, it's not, dude. No, you idiot! You idiot!
I'm an idiot. Oh, so I'm an idiot.
Yo, go down there, Donut, go down there, real quick, go, quick.
No, all my Vance, break me out.
Quick.
Vance, break me out.
I gotta break you out. We're gonna break you out.
Vance.
Oh,
Yes, kill him.
Yo, really.
Make sure your Fulbright's off because it's like supposed to be kind of scary.
Okay,
Just
yeah,
letting
it
you
is,
know.
it is.
I mean, I'll follow you, but
Oh, is
I
it
won't
standing?
really do anything. No, it's not, dude. No, you idiot! You idiot!
I'm an idiot. Oh, so I'm an idiot.
I'm going to kill Dr. Donut with a tree. Let me explain. You see,
Let's do some object detection with Python in 60 seconds. We're going to use the open source package YOLO v5, which makes object detection really easy. First, all we have to do is git clone this repo. Now I can cd into this directory, and in this directory there's a Python file called detect.py. We just need to call Python on this detect.py file. We can provide it weights and the source, which is my second webcam here. In a few seconds, a window comes up showing object detection. This model comes pre-trained on specific objects, but you can train it on your own data set. You don't have to use your webcam, you can run it on a video file. Just add view image to see the image as it detects. This footage of a car driving shows all the detected objects. Subscribe to my channel to see a longer YouTube tutorial on running object detection. Let's do some object detection with Python in 60 seconds.
This is one of the quirkiest and weirdest commands in Linux, but actually I think there's a few good use cases for it. Let's talk about the yes command. Now, yes is a command that will print out a string forever until you kill the process. Pretty weird. But if you add a string to the end of the yes command, it'll print out that string forever until you kill the process. Now, how could this be useful? Well, I could think of three ways. The third one is, I think, really cool. Now, the first reason why I think yes can be useful is if you're practicing stuff on Linux. Let's just say you want to practice killing your processes on Linux. I can type yes, and in another pane, I can grep for yes in my processes, and I can copy and paste the process ID to a kill command, and there we go. I have killed the process for yes. That's pretty neat, but I think there's other really cool use cases. Now, the second way I think yes is useful is if you are trying to work with a lot of data on your machine. Let's just say I pipe out the word something to a text file using yes. If I let it go for just a second, kill that process, I can now cat that something.txt file and pipe that to word count line. Now let's see how many lines are in that file. Wow, that's a lot. The yes command really pumps out a lot of stuff all at once, and it's fun to sort of work with large files in Linux if you're trying to do some interesting things there. Now, the last but most interesting use case for yes is dealing with annoying scripts. Let's just say I have an install script and I have to hit yes for every package I want to install. And then it takes a while, I hit yes to install another package, yada yada, so on and so forth. That's pretty annoying. But with yes, I can just pipe the output of yes to that install command, and it will install all my packages automatically because it'll constantly be saying yes to everything. Subscribe for more Linux tips and tricks, and hey, thanks, nerds. This is one of the quirkiest and weirdest commands in Linux, but actually I think there's a few good use cases for it. Let's talk about the yes command. Now, yes is a command that will print out a string for
Cô tầm mấy phút này cũng nhỉ? Rồi chúng ta cứ 3:10 nhá. Rồi 11. Okay.
Sao để tách phải hai cái len này là thằng này là 167, thằng này là 164, 167 là thằng này 183 rồi thì anh tắt cái len ở chỗ nào ấy?
Vâng, thì em xem chân mà đứng lên trên một chân thôi, cái đầu nó 164 thôi.
Vâng.
Rồi thêm một cái network nữa đó, thêm xong rồi nó bắt đầu là như vậy thế này có con vào đi cho tên là chỉ đi vào đi hay cho tôi đúng
Sao tạo đi
ở đây đó, ví dụ đó chúng ta phải chỉ phải 12 hoặc 2 đúng không? Ví dụ cho một tổng nữa, ví dụ là số đó bây giờ này tôi chỉ lấy số này nữa, tôi sẽ vào cái này thôi. Rồi bây giờ thì học vào phần hết từ phần trong cái phạt cái thuốc thế này thuốc vào là cái đầu sau khi làm việc cái bài có xưa một cái cân 183 của nó ở đây là cái sẽ tìm interface xung quanh server lấy cái sở liên toàn ký hình như là interface thì mình có phát thì đơn giản nó chưa lại chứ người nhé tôi thì bây giờ chỉ có chia cho những cái luôn nói tôi có gì rồi 164 cũng là ma mình này em nhớ không nhầm là nó phải chim sổ đúng rồi em thấy đang sản sinh một bộ nhưng nó vâng nó là tao còn thấy được rồi thì em cho nó ngồi đúng không được vâng nó trang nghe nó đang trả trùng thì số trang mới thả chung được đấy kia 197 nhá đó em 7 7 cái kia mình xem đấy là cái kia rồi thì mình cái này là cái gì sản xuất chất xử lý hết phần này của chính này chọn default để đeo em cho anh chọn default về đấy nó có chết không anh chọn vào đấy liệu nó không đi được nét nó có ngỏ luôn không rồi anh vào phôi nó xin chỉ để nói chung là anh vẫn còn chân để anh vào đúng không và trực tiếp phía bên xin mất rồi sẽ từng nhiều luôn chúng ta được cái này cho đi follow lên thẳng chấm 1 rồi đúng không xin vào lại mình đang chấm 1 rồi thấy đâu anh thấy rồi mình có lúc chọn ở đây lại nhỉ cái con kia thì cứ đặt là được con này đặt sẽ không được
What the hell bro is doing?
Phát triển phần nếu mà thử cái chân cũ thì rồi IP thì anh sẽ không vào được đúng không? Đúng là cái chân cũ đang 1.7 anh đổi về IP 100 thì nó có chạy được không? Đó, cái chân mà gần đấy nó sao ví dụ cái chân 192 này anh trên IP về thành chấm 5 thì được không? Thì sao không vào được thiết bị gì? Nó cũng như confirm thì em muốn đổi chỗ nào thì đúng rồi đổi chỗ thì đổi chỗ không thì cứ tại vì thằng đấy em đã thấy được thằng Management thì đang được anh chỉnh nó lại không nói chung là anh vẫn có một cái chân luôn nên sau bắt đầu họ nó chưa nhiều ở chậm điểm 3 giờ 10 nói chung là anh không phụ thuộc vào chân Management đấy anh có thể đổi nhưng anh vẫn vào được đúng không? Anh vào trực tiếp chỉ con nó SC vào từ con lại thế nó có cái chân từ con server to để từ con server vật lý để anh vào đúng không? Ít gì để vào được đúng không? Lại mình lại chỉ xin vào tôi là 101 làm từ từ nhé và đánh vào ba việc lực chỉ để một chút em hiểu sự khác chúng ta không phải những tên từ đúng không? chân kia đâu vào được gì ở đây đâu.
Nhưng mà cái chân 101 đấy thì không vào được ấy, thì nó chỉ là chân đấu nối để nó hứng traffic, cho nên là nó sẽ không vào được quản lý đâu. Không vào được.
Chỉnh để ra nó ở chỗ học.
Anh rút phát thử xem nào. Có cái lệnh là để câu để rút đâu. Rút.
Đi hết đây mình
Qua điểm.
đó cứ ấy rồi. Cà phê nó cái nó có cái thứ cái này nó nhiều ăn rồi thì nó sẽ nó ăn cả nó không nó để nó rồi biết tới chuyện
Bình thường làm con này nó vẫn cho phép tạo nhiều interface như này được đúng không anh?
cái chân nó cái phê này thì bây giờ nó phải đi
Anh thử cây thử để em phát này. Và còn tới chân internet thì em để upgrade cho là có thể là
xây dựng đó làm này
về internet. Nếu không thì anh có phải trên về cái trên trả về cái chân kia xong anh upgrade đúng không? Là
chúng tôi viên đang tranh đổi đúng thì chúng ta phải thường xuyên tìm lại lên về có tất cả lên về đủ xong để tìm thấy cái ra được thì cái là đường sau thì em để phải có một vài lần cần một con không có cái gì không có cái là gì 7 thì nghĩa là delay 10 ngày đó. Delay thực tế là 20 tháng 7. Và delay xuống ngày 30 tháng 7. Đến 30 tháng 7 là thì bắt buộc là sau 30 tháng 7 mình mới bắt đầu test RTB rồi đúng không? 30 tháng 7 đó thì trong tuần cái gì là nó vậy cái mốc timeline em đưa ra chứ không phải là bên em đưa ra mà là bên anh đưa ra, bên em nhìn mốc đấy để theo dõi cho anh đưa lại của em cả. Vì bây giờ mốc đấy không kịp rồi thì mình đang trễ mất 10 ngày. Không anh, những cái thông tin mà anh em đang thay đổi trên file plan này, thì khi anh em thay đổi thông tin ấy, thì khi nhìn vào plan là một người mà chưa không follow là không biết được là đang thay đổi được như nào đâu. Tuy nhiên là bám mục tiêu đưa ra thì không ai một trễ cả. Nhưng đến khi nó trễ rồi thì trong file plan anh em phải thể hiện rõ là nó trễ như thế nào. Bởi vì một người mà chưa follow dự án thì mình vào file plan thấy được và đang bị trễ thì như thế. so với dự kiến là hiện tại thì anh em đang cuối năm 30 tháng 7 của em còn đang phân vân là không biết nó có bị đâu nữa hay không, vì thế là cái đúng rồi, cái mốc 20 tháng 7 là không phải là mình đưa ra từ ban đầu đâu, nhưng mà nó đã trôi từ đầu tháng 6 rồi thôi. Đây là cái nguồn. Cái đấy thì nó cũng hiểu, nhưng mình đây anh em cũng cần được thông tin vừa nghe rõ với nhau. Rồi. Thực ra là cái vâng thì như em có trao đổi là timeline đưa ra thì anh em thì follow thì không ai muốn là timeline bị trễ cả, đến khi nó bị trễ rồi thì trong cái lúc mail alo cái là không chỉ có cái nó sẽ một cái mà nó không chỉ là cái đó chỉ là để ra đâu chỉ là anh thông tin thêm nhé, cái file hôm nay của anh Huy thì là cái file mà hãng gửi phản hồi để cần nó bên mình confirm đúng không anh? Tôi cái chuyện rồi thì trước đấy khi anh em trao đổi luôn đang thấy là anh em thông tin trước đấy là đã chốt file thiết kế với hãng rồi, bây giờ hãng chỉ cần cố gắng cài đặt thôi, nhưng bây giờ mình lòi ra một cái task là hãng gửi lại cái file để mình confirm lại. Thì chỗ đấy em đánh giá là anh em trong đầu chưa nắm được cái task này, những cái task này nó phát sinh nó cứ kéo dài thế mà triển khai như nhưng ở đây phải chốt lại và là những cái thông tin anh em trao đổi với hãng, anh em số rằng những cái phát sinh này chính sau bắt đầu cũng không biết được, nhưng dẫn đến là các timeline nó bị delay như thế đó. Vâng, chỉ về mặt FPT bên em đang đánh giá là như vậy không. Trong file plan thì anh em cũng không thể có cái tab là hãng gửi lại file vào review lại, không thể có cái tab đấy trong file plan bên này, mình không theo dõi được cái tab đấy, nếu nó phát sinh là chỉ có mấy cái chữ thôi phải được. Trong cái lúc mail mà Trung Dũng gửi thì em không thấy những thông tin rõ là timeline đang trễ đến ngày bao nhiêu cả, cũng chỉ nói chung chung là vẫn hoàn thành cái tham gia chung tiến độ chung của dự án thôi. Như là phải có đúng rồi, thì bây giờ bọn em muốn là những cái thông tin qua mail ấy, trước đấy mình đã đưa ra vào 20 tháng 7, hiện tại nó đang bị đây chính là 30 tháng 7 anh em phải hết rõ thông tin timeline đấy ở trong nút mail để tất cả những cái nắm trong thông tin đấy thì cái gì tiếp đi Với lại S7 lab đi, S7 Motion thì bọn anh hiện tại đang trễ như này, bọn anh đang trễ lên ở timeline lên S7 Motion, mình chưa đánh giá được cái này bao nhiêu, mình lên được S7 Motion. Có những cây ở trong ATV chi tiết cụ thể của anh phải nốt vào, cần code trên S7 Motion thì lúc đấy phải code trên S7 Motion. Đúng không? Cây S7 lab không đáp ứng được của anh phải nốt code trên S7 Motion này. Đó, từ lúc mà S7 lab tắt ok, xong S7 lab ok thì mình dự kiến đi 10 đến 14 ngày. Vì nó còn liên quan đến thủ tục đưa lên kế hoạch lên chứ phải anh tắt S7 là tắt luôn rồi đâu. Các bên khách hàng console những thứ của anh ấy tác động đến hệ thống, hệ thống đang chạy phục vụ xin tắt trên S7 nó xin thì bọn anh cũng không nhận chung được đâu mà phân. Không anh, còn những cây tốt anh bắt buộc phải test trên S7 nó xin của bây giờ anh đang trao đổi thống nhất cái file TV với đối với anh ấy thì có cái đánh giá đấy vào cái file TV là chưa thống nhất được thì anh chưa đánh giá được. Đó. Đúng rồi. Cái này thì như trên trao đổi đấy, mình đã trao đổi rồi. Đấy tham gia trước thì là khớp, còn bây giờ đang trễ như này thì phải trả cái đánh giá như nào luôn. Thời gian này thế là cái thông tin là bọn anh đã thông tin từ trước mà, chứ không phải là hôm nay bọn anh mới thông tin đâu, nó đánh giá là nhiều hay ít. Trước đây là anh đã thông tin rồi, anh em có cái nội dung meeting anh em nốt không đầy đủ nên là nó hơi bị ít. Còn cái timeline mà S7 trong file plan là anh em đang đưa ra đây này, thì anh có nốt và trao đổi với rất nhiều lần là cái thông tin timeline đi nó phải có trình nó sẽ thay đổi và phải đẩy lên trước cùng với cả S7 lab, hay không mà phải thuộc vào kịch bản tất cây ITV khi chốt anh có trao đổi rõ như thế được mà. Hỏi thì có cách trình được tin được không? Biết là những tin sẽ cái thứ ở đây là ở hiện giờ thì đấy là phải hiểu rằng là không rõ. Trước với kinh nghiệm luôn em ấy, đánh giá ít nhất cũng phải 14-15 ngày. test là việc thu thì nó có cái vo voi Thế là kinh nghiệm trên bên em đánh giá cái con năm sau bắt đầu em đánh giá là 7 ngày thì em thích biết là thế nào. Còn cái lịch mà đưa lên S7 Fusion ấy, thì em đã đưa rõ là cuối tuần này theo lịch là làm em sẽ lên S7 Fusion ở Hồ Chí Minh, trong tuần sau là đi S7 Fusion ở Hà Nội. Còn hiện tại đang không đưa lên được nên là đang với cái chỗ mà không chưa triển khai xong để test S7 Lab nên là phải đi lại thì tham gia đấy nghỉ ngơi thế này. Chưa bao thì bọn em bốc là trong tháng 6 rồi nó bị khóa nó tham đấy rồi kia bắt đầu em đưa ra là trong quý 2 là đưa chưa bao vào thì kia sẵn sàng, hệ thống sẵn sàng để chạy đưa dịch vụ khách hàng vào. Chỗ này thì để có thuê bao vào hay không thì bọn em không biết trước được, bọn em chỉ biết được là mong muốn ra sớm nhất hệ thống hoàn thành để sẵn sàng khách hàng vào chạy dịch vụ, để bọn em lấy cái thông tin đấy đi trao đổi với kinh doanh là ở cái mốc này là sẵn sàng cho khách hàng chạy dịch vụ thì mới được rồi em chạy được của anh nên hiểu ý bên em không sát được, chứ bên em không thể nào cam kết được là khách hàng có bao nhiêu khách hàng chạy được, và chỉ cam kết được là tại cái mốc này của em mong muốn đâu thì hiện sẽ sẵn sàng cho khách hàng vào chạy trực mình. Để khách hàng mà chạy được thì bắt buộc phải quét hết các kịch bản thì của em mới confirm thì là khách hàng chạy được. Như là cái tham gia của BMCM đó. Tiếp là tiếp để mà đưa tiếp mà để đưa khách hàng vào thì biết trong ngay của em đã báo cáo đây các tích mình giữ là dự kiến là rất là sau lần có người đưa hàng vào đây sau đấy thì mình đi lấy thì là nó văn thành bây giờ đi lấy thêm một lần nữa này thì của anh chỉ chia giá hứa tiếp là ngày có thể ngày nào đến nhà được thì chung vào chính thức những trên những như là tiền lên nhất thì chỉ phải được của mình sẽ được cái việc và rồi như là họ người cái thứ về nếu mà để online triển khai của bên anh có thể đảm bảo được cuốn tủ nó đúng ngày nào có thể thì trong nhiều nơi làm cho mình như bây giờ thì là phối hợp giữa các bên, nhưng mà bây giờ các bên thống nhất online thì bây giờ quản lý là xem thử là bây giờ dự kiến đến bao giờ cái thời gian trả thì nhất có thể từ thăm hàng để thẩm duyệt và bao giờ để kiểu để như là cái thì chúng ta còn đưa theo được cái việc có cái việc nó sẽ lúc này thì như em thông tin với anh Minh để mà 30 tháng 7 là xong này, 31 tháng 7 là bắt đầu test đúng không? Thì ngày 30 tháng 7 là deadline mình phải hoàn thiện được các task để chuẩn bị trước ngày test ATB thì là hai bên phải chốt được kịch bản ATB này và song song với đấy là cái tài liệu mình là HLD nào và cái bên này có đề xuất trong lúc mail là sau bắt đầu chuẩn bị cái hệ thống Quick chỉ hiện ra kịch bản các kênh trên hệ thống có hai cái ba phần đấy thì mình phải xong trước ngày 30, deadline là ngày 30 thì mới đảm bảo là 31 mình bắt đầu mình vào các kênh đấy. Như từ trước có trao đổi với anh có những kênh nó liên quan đến các HA liên quan đến thiết kế thì mình phải thống nhất được thiết kế thì mình mới đưa ra thiết kế để mình sao thiết kế được. Đang tìm nghe đấy. Anh bảo là thì anh bảo là giả dụ ATV nó có 30 tất cây chẳng hạn thì nó có trong đấy thì điều đấy như thế nên cái chỉ tạo ra tức là hai bạn nên mà nhiều phải phá lên được vào không giao như thế này cô giờ bọn anh ấy đồng ý cái việc là trong thời gian mình có thể bắt đầu test ATD và xong thời gian đấy mình hoàn thiện cái file HLD thì anh em phải chốt được file HLD làm sao để phép được có những cái chất cây mà trong ATD ấy, cần cái file HLD phải chốt trước để test thì anh em phải estimate làm sao cho nó chốt cái timeline đấy. Chứ bây giờ anh em đang test ATB giờ đúng không? Bởi vì còn 5 cây không test được do không chưa chốt được file HLD. Nếu đấy của anh cứ chờ file HLD mình phải kiểm định bao nhiêu 5 cây rồi nó chơi. Biết gì cái điều tiếp thì mình biết được cái này một cái điểm đó cái gì đó khi mà ở dân thì tôi Trên sửa thì bọn em mất quá nhiều thời gian rồi để tin xong được rồi. Bây giờ đúng là 30 mà. Anh có xong để không phân tích anh em phải cần phải thông tin gì được không? Đây, bọn em hiểu, bọn em vẫn khả năng đồng ý với việc là mình chốt cái bản test cây LTV bắt đầu vào test song song với thời gian đấy mình hoàn thiện cái file HDD thì bọn em vẫn đồng ý cái phương án đấy mà anh em thì nhưng có những cái test cây mà cần xong HDD thì anh em phải xong phải hoàn thiện hết các test cây chứ không phải là chờ HDD xong thì mới bắt đầu vào test LTV. Và mai mình sẽ chơi đỏ mình chỉ cần mình ngon vậy ngon còn nhiều ăn được được ngon anh chưa được chọn đấy là cái vấn đề mà yêu cầu là tôi phải chuyển đấy cái phần tiền sử và mình sẽ chuyển sẽ phát mình chuyển chỉ thị đó mình chuyển sản xuất mình bán sản đó rồi phần tính thiết kế là mình đã gọi là xong là đã sử dụng và có nữa hay là có vấn đề thì mình không hoàn thiện sẽ đã ao đấy. Rồi bây giờ ATT nó phụ thuộc vào ATT nó phụ thuộc vào cái chết. Nó bắt đầu tiếng Trung thì cũng có HA không? Nhưng mà A thì nó chảy như thế nào thì nó chảy nó kiểu A nhưng mà đến bây thì nó mới xử ra là nó có thành phần thì nó có dùng follow chảy thì nó như thế nào mới ra chẳng năm nào thì ở trong cái thiết kế khi mà triển khai thì bao gồm một số thiết kế đó thì mình mới define được cái state play OTT và hóa số đang gọi là cái form như nào FTC 1 hay FTC rồi ví dụ như tôi tạo cho cái nào đó thì nó sẽ dừng thôi đâu cũng phải quá triển khai và rất là đảm được còn nó không muốn cho con từ biết không làm nó có từ bất sử dụng thì mình phải chuyển lại cái nó phải theo là trong hai sự đó và còn ra thì bảo cơ bắt theo cái phim của đất thì bảo ta là con nó có HA đúng mà nó biết nó chảy từ như nào
bây giờ nghĩ ra nữa hỏi rồi là biết rồi
rồi thì nó mô tả là trong cái test nhưng mà cái bài test nó phải dựa vào cái phần thiết kế thì nó mới file ra được cái bài test rồi chỉ bây giờ thiết kế bây giờ những phần đấy mình đã chốt mình đã thống nhất được những áo chưa mình xong luôn chỉ cần nó cái gì mình cho xin cái kho không phải như hôm trước anh em có review một cái gì như cái thành phần con ETCS hay con gì đấy còn chưa có trong mô tả kia có những cái phần đấy thì anh em đã bổ sung chưa? Đó người tin bây giờ chỗ đủ bây giờ con phương cái thành em thử là những cái phần để chưa phải là những cái phần bên bản tình bằng không hay là có cái việc gì nó yếu thì là nó chưa đầy đủ mà để mình chưa nói cái công việc để mình có thể là được bay test với mình ông là một sự nó rất là từng phần việc thì mình là dùng cái đó là tuần trước mình cũng họp mình cũng ra nói nhưng mà ra nói qua cái này từ tuần trước đến giờ là mình chưa có một cái vơ với trước nào nên là mình có cái tổng lời mình tìm tạo những cái chạy các nó có thể trong timeline thì đấy nó dự kiến là 21 thì sẽ cho mình để mình chung kết nhưng mà chưa đến nhân lực khi nào mà cái buổi họp một chút trao đổi xong thì là các chương trình rất là sau đấy thì một thực hiện xong hôm nay làm như là trao đổi và sẽ người với mình thì sẽ lại nếu mà mình chưa kết lại thì mình phải ra đi còn như học sinh thì không bị stress anh làm được để xin chỉ sau đó mình sẽ đánh vào mình có mình thêm Anh chưa đủ thế nào đấy. Ok. Người biết đến sao chưa cái gì thế nên chung cũng là có biết cái lúc này nên sau đầu cũng có đủ cái khổ sao nó đúng rồi Cái chỗ file tài liệu HLD là bên này là bao gồm DLD luôn rồi mà. Cái được tổ chức kênh thì biết nào thì phải có được chơi lại. Đúng không? Đúng không? Có nghĩa là file tài liệu anh em sau bắt đầu sẽ gửi file HLD nó đã bao gồm DLD và HLD rồi, đúng không? Ok, và file LLD kia nữa rồi. Ok, cái đấy là anh em trao đổi chốt thì hôm trước thì mà anh em đã sau bắt đầu đang gom là HLD nó bao gồm cả DLD trong đấy luôn rồi. Bây giờ các cái mục tiêu, các cái đầu mục mà anh gửi DLD cần có những gì thì anh em đã nhận thông tin và để cập nhật rồi thì bây giờ anh em cập nhật vào file HLD rồi được gửi cho anh HLD với cả LLD. Đó, cái khóa học thì tuần sau sẽ là 1/8 nữa. ATV buổi 1 nha. API buổi 1 không? Chỗ này thì bọn anh chung bận thế. Cái đấy bọn anh chưa nhận được email đâu. Cái theo là mình không được cái chỗ mà liên quan đến đào tạo ấy, thì bọn anh cần thông tin là nội dung cái buổi đào tạo của từng buổi đào tạo này. Mục tiêu nội dung và tài liệu thì để đánh giá là cái buổi đào tạo đấy pass ok hay không, not ok. Cái đấy phải gửi trước sớm trước cái buổi học cho bên ông. Em đúng xong các thông tin trong buổi trao đổi hôm nay, xong rồi em ghi cả cái nội dung buổi để trao đổi vào lúc nào. Nó lúc này em còn cái một phần nào trao đổi đúng không? Đó là nhất một nhớ đó có chế độ nếu là không được còn một tàu tình bạn những lúc là một nhớ lại khi mà gọi mình có một chút hình chung do chút hình phải làm quan đam mê một chút gì hoặc là đi cái hình là với sự đi với đi bàn là những cái sao những các làm phim cáo về làm những cái ok, nghe được rồi. Em vẫn nghe được không? Thì anh Linh ở đây là từ ngày 30 tháng 7 mình chưa chốt được hết cả kịch bản NTD hay sao? Để phép được chốt được kịch bản nó lên xem có những cây tốt nào tốt trước hôm 31 tháng 7 bắt đầu tốt thì cái sau thì cái đấy để chốt được cái file kịch bản thì mới nói được. Trong cái tượng đài các cây đấy có những cây còn chưa define rõ các thứ nên mình phải chốt được tất cả bao nhiêu cây define được cây nào tốt, chốt cây nào tốt trước, cây nào tốt sau cần define hay như thế nào đấy thì có những cây là chưa có, bọn anh có tuần trước trao đổi với anh có phản hồi đó thì không biết là hôm nay hôm qua đủ trao đổi với cả bên chỗ Hùng đang update nhỉ, sâu luôn file ra. Cái này đấy